Okay, hi everybody. Just to start things off, this is my first live stream. I've never done any kind of stream before, so you would have to excuse if there are some technical hiccups or other fuck-ups. I'm sorry in advance. And just to start this off, ideally, could you maybe verify a few things for me? Like, first of all, could you please comment if you can hear me, which I hope, and then could you please comment that you see my nice intro sheet here. And then also what I will do is I will switch over to the second kind of view, which is going to be this circuit simulator. So it would be great if you could tell me if you can see my browser window now. Okay, perfect. That sounds good. Then, welcome everybody, and let's begin. So, okay, first things first, why do this stream? Well, basically I got the idea from you guys. So there were a bunch of comments and messages of people asking how I did the drum sounds in the diode filter video, which, I did this demonstration song, and I claimed that I either filtered all of the sounds with a filter or I created them with a filter. And of course, like, the filtering itself is probably self-explanatory, but the drum sounds might be, like, to some, might not be that obvious. So people were asking how I did that, and that got me thinking. Of course, you can use a filter module to make a drum sound, but you need an external envelope for that, and you need to set it up properly and everything. And I thought, like, what if we could build a circuit and that's kind of based on the filter, and that is a standalone drum module. So the goal there for me would be that we have a circuit that we can feed a trigger, some kind of trigger signal, and that for each trigger basically puts out a drum sound. And yeah, so that's what I will try to do in this stream. The thing is, I've thought about it. I have some ideas of how I want to go about it, but normally, like, in my videos, I have like a clear laid out script and a plan, and I know what I'm going to do. But here, I'm going to kind of show you what my process is. Like, I'm going to try to show you, like, what I'm thinking of when I'm creating a circuit. And yeah, that's basically the goal here. So first of all, we should probably start by talking about how I got the filter to create or to make the drum sounds in the first place, because this might be not so clear to everybody. So let's begin with that. So, okay, so the first thing is going to be how can we make a filter make a sound on its own? Like I said before, of course you can filter other sounds, but the question is, how do you turn your filter into a module that creates an oscillation? And it's actually quite easy. You just crank the resonance up. That's why I drew the knob here, at maximum setting. And what that does is basically it sends the filter into safe oscillation mode. So then the filter will just, basically turn into an oscillator and just create a tone on its own. And once you do that, once you send a filter into safe oscillation mode, then you can use the cutoff knob basically to set the frequency of the oscillation. Because I mean, I went over this in the dedicated resonance video, but basically, I mean, what it does is you set the cutoff frequency, and then the filter will start oscillating at that exact frequency. And so, of course, if you just take the module, you connect your output to your speaker, you send it into safe oscillation mode, you turn the cutoff knob, you can select a frequency basically, so you can tune it to a note. But what you, of course, can also do is you can use CV. You can use a control voltage to set the cutoff frequency. And that's kind of what I've drawn here. So, I mean, these values are imaginary, but if you take a lower value for a CV, then you are going to get a relatively, low frequency oscillation. And then if you increase that control voltage, then the frequency of the oscillation is going to increase, basically. But still, like if you send in a static control voltage, of course your frequency is also going to be static. But now the question is, how do we kind of turn like a static tone into something that sounds more like a drum sound? And I don't know, like maybe some of you have looked at drum samples in your DAW, like in Ableton or something before. And usually what you see when you do that, usually when you look at a sample, at the waveform, you're going to see something like this. I mean, this is not very well drawn, but like the basic idea is just this, that you are going to see a very high frequency oscillation in the beginning, and then it's going to basically lower in pitch very, very rapidly, and then it's going to kind of stabilize at some kind of base tone or frequency, and then in the end it's going to drift off. And that is usually how a kick drum or even a tom will look like. And now this is kind of complicated to decipher because, I mean, it's hard to kind of visualize it from this waveform. So the question is also like, what do we need to feed into the CV input to get this kind of response? And to make this a little bit more intuitive, let's look at another sheet. So, as you can probably tell, I am very bad at drawing round shapes. Like usually I use the dots on the paper to kind of guide me, but in this case, I mean, I had to draw a drum. A drum has to be round, and it looks a bit, I don't know, off. Actually, we can think about adding noise, David, but I mean, let's see down the road. Okay, but I was here. The drum looks a bit shitty. I'm sorry. But if we want to make a drum sound, we should first talk about like, okay, how does an actual drum sound? Because I mean that's basically what we are trying to model. And so if you think of like a real drum, like in this case it would be a tom or even a bass drum, then you basically have, I mean, you have this cylinder shape. You have a drum head on the top, and you have a drum head on the bottom. And there's obviously air in the middle between them. And those heads are made from mylar, I think. It's some kind of plastic. And what you would usually do with a drum is you would take a stick and you would hit the drum, obviously. And so what happens then, I mean, this is really overly simplistic, but we can kind of divide the sound a drum makes up into like 2, maybe 3 phases. And the first phase would actually be when you hit the drum with a stick. And the situation is that you have a stick that's made from wood mostly, and then you have this drum head that is made from plastic. And so what's going to happen on impact, like when you in the moment that you hit the drum, you're going to have this smacking sound that you also can get if you smack your hands together, like this, which is like very quick. It's like instantly there, and then it's instantly gone. And that's actually also what happens when you strike the drum. And what happens then is that after that, or maybe simultaneously, but what happens then is that the drum head starts swinging basically. So the top head starts oscillating, and what that does is that starts to kind of move the air inside the drum, and that starts to move the bottom head. And so after that initial, like this quick smacking noise, you have like the actual tone that the drum produces, which is usually much lower in frequency than that initial smack. So, and also it will last longer because, you know, the drum is oscillating and it takes some time until that dies down. And then one more thing, I think this is kind of like a question of how you tune your drums. I think a modern sound would have like both heads tuned to the same pitch. So the tone of the drum would be just one note, and then it would just get quieter and then die down. But what people used to do in the 80s, I think heavily, is they tuned the bottom head to a different pitch than the top head of the drum. And what that did is that gave you a drum tone that kind of started at a higher pitch, and then it kind of dropped down like to a lower pitch. It's like very characteristic. You can hear it in a lot of 80 sounds. It's like this doo sound. Sorry for the bad impression. And I feel that many drum machines seem to be modeling actually this kind of sound, you know, where the pitch of the drum is kind of dropping down in the end. And so that is basically also what we are going to do. And so knowing this now, like knowing what we want to model, we can think of, or we can kind of try to visualize this better. And so what I've done here is I've drawn this graph, which is very simplistic, but the basic idea here is that on the x-axis you have time, and on the y-axis you have frequency, basically. And then what we can see is we start off kind of instantly, like we have this instant rise to this kind of peak up here, which would be, you know, just a smack. And then the tone is going to drop off very sharply because, like I said, like this initial smacking is just very short-lived. And then what happens is that the drum starts oscillating at its base pitch, basically, and that would be this phase over here. So then the frequency drops down to this kind of pitch of the drum, and then in the end, like I just explained, the pitch is just going to, you know, die down and then drop off. And I guess most of you already know what I'm getting at here, because obviously the next question would be, okay, so if we need this shape, the question is, how can we create this shape? And you might have guessed that, of course, we are going to use an envelope. And specifically, I mean, what I used for the demo song was an ADSR envelope, so attack, decay, sustain, release. And the idea is basically you can, with such an envelope, you can generate a voltage curve that is split up into 4 different sections. And in our case, when we try to create this drum sound, we are going to want to have like a very quick attack. So that means the sound should start off immediately, because of course, like a drum sound has no build-up usually. When you hit a drum, there's no build-up to the hit. So you hit it, and then instantly the frequency has to jump up. Then what we need is we need this decay phase. So we need to drop down from this peak voltage to some kind of sustain level. So this is going to be the frequency level at which the drum is going to sound. And then in the end, we basically need this kind of release stage, you know, where the sound dies down in the end. Okay, so first of all, what I want to do, like now that we know what we are set out to do, I am just going to get out the breadboard. I'm going to recreate or try to recreate the drum sounds from my demo video, and then we are going to, I'm going to do this using an external envelope. And then after I've shown you like how this sounds, how it works and everything, then we're going to go into the actual circuit design. Now, one thing before I show you the breadboard, I have already taken the liberty to cut the circuit down a bit. So basically what I've done is I removed all the parts that are unnecessary, stuff like the input audio processing, like we don't need that, and several other things. We are going to look at that also, but for now just accept that the breadboard is a bit more barren than it used to be in the video. Okay, then. Okay, so I hope that the breadboard is visible. I guess so. Okay, so first let me connect my power supply. At this stage, I've recently, like, we like on the Discord server, we had some people saying that they had problems with their self-built power supplies. And I just want to advertise, like I recently bought a decent bench power supply, and the cool thing about that is it has a current limit, which is super cool, because if you do something stupid, if you short something, the power supply will kind of detect it and it will just shut down, like it will just stop pushing current out, which is extremely great because you're not going to see any smoke, and it's really nice. So if you have a low tolerance for frustration, or if you don't want to burn your house down, then I would really advise, especially beginners, to get a proper bench power supply. Okay, now I have to remember this one is negative. Okay. And this one is positive. Oops, I'm sorry. Okay, I tested this before I started the stream. Let's hope that it still works. Ha, it works. Okay, so like I explained before, of course, what you can do is you can change the pitch with the cutoff knob. Oh, Schreibmaschine. I went for, it's called the PeakTech 6300. It's kind of, it is actually a symmetrical power supply. Like it has the plus and the minus output, and you can change the voltage on the fly, which is super handy actually. Yes, true. The symmetrical ones are pricey because they're kind of rare. This is actually the only kind of a decent one that I could find. So, sorry guys. Okay, so like I was saying, you can of course set the frequency of the self-oscillation with the cutoff knob, but this is never going to sound like a drum because my fingers are just not fast enough. So, what can we do? Well, easy. We use an envelope, and sadly I don't have a second camera, so I would like to have a second camera on my modular, but I don't. So you're gonna have to trust me that you know I'm using an envelope. Okay. Okay, that doesn't sound like a drum, but you can hear that it's, you know, it's kind of in the ballpark. Brandon, this is actually, it's not an oscillator really. It's a filter, and it's just based on these diodes. Like these diodes in combination with these capacitors are basically what create the oscillation. Okay, so like I was saying, this doesn't sound much like a drum. So what I'm going to do is I'm going to change the parameters of the envelope to make it sound more drum-like. Okay, so you can instantly hear something that doesn't sound right, and maybe hard to describe. But what I found is the problem with this kind of setup is basically that. Give me a second. If we look at this graph again, what's happening right now is that this peak is extremely high up. So my envelope will, I think the peak voltage is something around 9 or 10 volts that it will push out. So what happens right now is that the frequency jumps up extremely high and then it drops down very low. And the thing is that what, my stream ends? I hope not. Okay, let's see. So what happens is basically like we jump up very high. I mean, of course, guys, like this is kind of up to taste. Like you can of course use this as a drum, sure. But what I found just for my taste is it sounds a lot better if we kind of take this peak down by a lot. And the way that we can do this is like I'm using a 47K resistor here to kind of feed in the control voltage. And this is kind of part of a voltage divider. And so there's noise on my voice channel. Yeah, I can bump my volume. I can try if it's too loud. Sorry. Okay, so I was here, yes. So this resistor I'm using is part of a voltage divider. So this kind of divides the incoming CV down. And with the 47K here, the voltage divider is not going to divide it down that much. So what we can do is we can replace this resistor just with a stronger one. So if I replace this 47K for a 200K, like that's what I tried earlier, then it sounds a lot better to me. So that's what I'm going to do now. Okay. Okay, so to me, that just sounds much more like a kick drum. And of course, if I play with the parameters, you can hear like now I'm kind of extending the release. So it's just, you know, more angry. I can turn it down again. And if I increase the sustain level, you can hear how the bass pitch of the drum changes. Okay, so this is basically just the basic idea. And now that you know that this works, we are going to ditch the external envelope because it's not what I want to use. I mean, a disclaimer here. Of course, you can just take a filter, take an envelope, make a bass drum. But like I said in the beginning, I would like to just have a standalone module that I can just wire up. I can just feed it a trigger, and I can have a bass drum ready to go. I don't have to set all this stuff up. I don't have to, dial everything in. Like that would be what I want to have. So first of all, what we're going to do now is we're going to look at what I've cut out of this circuit. And for this, we are going to switch over to this circuit simulator. I think most of you probably know this. Like I usually use this to make some sort of point, or recently I've started to, under my project, under my videos, I kind of post links to this exact page where you can then kind of play around with my circuits in the simulation. So, but if you don't know what this is like a very, very nice, very simple circuit simulator that runs in your browser. You just go to this page. You can usually find it if you just search for Falstad and circuit. And what you can do in here is you can put together a schematic, and then it will kind of simulate the circuit for you. You can use an oscilloscope to check what everything is doing. You can try out different component values. You can do all sorts of things. And no, before someone says this, of course, these things often lie to you. Like they are not going to be like super accurate or precise, and they can be misleading. Like they can show you things that don't work or that might work differently in real life. But generally, like for me, this is just a really nice tool to just try stuff out like really quickly. Because if you want to do all this on the breadboard, the problem is you have to get out your oscilloscope. You have to, get out all those components. You have to put them into the circuit. You have to try them out, and you measure the values, blah, blah. And it just can get a bit tiresome. And that's why just for the rough idea stage, I really like to use this simulator. Okay, so, but actually I just noticed that this is not what I wanted to show. What I wanted to show is here. This is a nice thing about this also. You can export your circuits that you've built in here as a link. And the cool thing is your circuit is not saved on any server. Like it's not on their page. The link that the site generates is basically, it includes the binary for your circuit. So it has your circuit in the link. That's why you use like this service to slim the URL down. But the cool thing is that the circuit is basically like when you save the link, you have the circuit on your machine technically, which I think is just neat. Okay, so I can't see comments right now, so let me check. Let me check if anyone said anything. Oh, okay. Okay, cool. So I hope you guys can see this. Okay, so first of all, maybe some people will be a bit confused because this schematic differs a bit from the one that I showed in my video, and that is because I've done some revisions to the circuit actually. I've made the filter into a multi-mode filter, so it can now work as a high pass, as well as a band pass, and as a notch filter. And then also I have changed the way that CV is processed and handled. And the upcoming video will deal with that in detail. So I won't dive into that now. Just one thing, which is kind of important for the whole drum thing. There was a rather annoying problem, which was basically, I mean, if you think back to how this whole thing worked, then if we really dumb it down, the idea is that we apply a positive voltage here, we apply a negative voltage here. Let me zoom in, I'm sorry. So we apply a positive voltage to the top of the diode ladder, we apply a negative voltage to the bottom, and then what happens is that these diodes start to open up a bit, and then we also feed the oscillation through here. And so in this scenario, we can use the diodes as voltage-controlled resistors, because the bigger the voltage difference between these 2 points, so the top and the bottom of the ladder, the wider open the diodes are, and like the lower the resistance value is, and so then the cutoff frequency goes up. And the problem in my original design was that it was possible for the voltage here to go negative. And this is bad because, I mean, if the voltage is positive here, why is this struggling so much? If the voltage is positive here, then the voltage up here will be positive, the voltage down here will be negative, and then you have this scenario, you know, where the current is flowing from here to here. But as soon as the polarity here reverses, so if the voltage here goes negative, then the situation here also reverses. So then the voltage up here will be negative, and the voltage down here will be positive, which in and of itself is not that bad, because of course the diodes are blocking. Like current can only flow in this direction. So if you try to push in this direction, then the diodes will just say, no, you won't, and they just block. And that works, that's okay. But what I've seen happen is if you had quick transitions between on the CV between positive and negative, or negative and positive. So if the voltage here swung from negative to positive, or from positive to negative, and basically the voltages here reversed very quickly. So this went from negative to positive, and this went from positive to negative, or vice versa. Then you had this horribly annoying clicking noise. I'm not sure if that's because, you know, of the transition from the diodes being completely, you know, blocking and shut to opening up, but that's what I kind of suspect was happening. And so I had to kind of do something about this, because of course, like with drum sounds, the idea is that you, as you've seen earlier, the idea is that you go from, you know, from kind of a low or maybe even a negative input voltage, like up to a very positive voltage, and then you drop back down again. And so in some scenarios, this resulted in some annoying clicking noises. And so essentially what I did is I just put a diode at the output of this op-amp. And this will block any negative voltages. So only positive voltages will go through here. And I mean, this was kind of a shot in the dark, so I just put it in there. I didn't think it would work very well, but in the end, it works fine, as you just heard. So that's what I've done there. Okay, so then what we're going to do is fun. I don't know why this is so choppy. Like, I just bought a new MacBook, and everyone is saying, oh, the M1 chip is like, ooh, it's crazy fast, blah, blah. And this is choppy as hell. Okay, but let's see. Okay, so if we want to get rid of stuff in this circuit, the first thing that we can look at is basically the audio processing, because of course we are not using the filter as a sound processor. We are using the filter as a sound source. So we won't need to put any audio into this circuit. So what we can do is we can just go ahead and delete this entire input stage, which saves us an op-amp, saves us, you know, a capacitor, an input socket, which is great. Okay, then what we can do, of course, we can get rid of these, you know, these switches I put in, which were used to activate the high pass, the band pass, or the low pass mode. And of course now everything's going crazy. Okay, so this can go out. Then these entire connections are unused now, so they can also go to hell. And then here you can see these capacitors were basically, I basically fed them the input signal to turn the filter into a high pass or a band pass. And so what we can do here is we can basically just revert this to the usual, to the old state, which was just having these capacitors grounded. And if they're grounded, then this will still oscillate and everything is fine. Okay, so what else can we do? Well, you can see like this connection here used to be connected to our input buffer. So we can be pretty sure that we can just take this stuff out because we're not using it anymore. Same goes for this resistor. Like if you remember, we used this resistor to set up this op amp to basically combine the offset voltage and the incoming oscillation. So, whoops. So if we delete this, then what will happen with this op amp is basically just that it will be inverting the CV. So because this is just a basic inverting op amp configuration, and now the resistor values here don't matter that much anymore. Like if they are identical, like this could also be 10Ks or 1Ks or whatever. Whoops. Okay, so this could be also 10Ks or 1Ks or 100Ks, whatever. But I'm going to keep them at 33 because, you know, it doesn't matter that much. And then, like I said, what this op amp is going to do is just going to invert the incoming CV. So the situation will be the same as before. We just won't have our oscillation riding on top of the bias voltage. Okay, so saved us another bit of a headache there. And then the next thing is, okay, so if we look at this op amp, this was, like the configuration of this one was rather complex actually, because we had to, like in this case, basically adding and inverting, or adding the CV to the oscillation and then inverting both was fairly easy. But in this case over here, we had to invert the oscillation, and we had to add the CV without inverting it. Won't get into it right now, but that's why this was basically a bit more convoluted. What I found is we can basically, I mean, because like I just said, like what this did was it took the oscillation, it inverted the oscillation, and then it added the control voltage. But now, since we're not using the oscillation, we're not feeding the oscillation in here, all we need is we just need the control voltage, and we don't even need to invert it. We don't need to do anything with it. So what we can actually do is we can say bye-bye to all of this, and we can just straight up wire this here through a 2K resistor. And if you think back to that video, you might remember that I only just used the 2K resistors here and also here to make sure that in the case that we push so much voltage or so much current through this through these diodes that they open up completely, we want to prevent that we get a short circuit. So if for whatever reason these diodes really open up and they basically create a short between these 2 points, then having the 2K here and the 2K here will ensure that these op amps will not be shorted, basically. So these are really just to protect the outputs of the op amps. That's just their purpose. Okay, so let me check the comments again. Sorry, I have to jump up and down. If I drag a rectangle and pointing, my mouse pointer is not visible. Ooh. Okay. Okay. I will try to draw a rectangle. Okay, but like I said, what we can do here is just delete all of this, and this makes our circuit already much more manageable. And then there's actually more that we can or that we should do to make this better suited for the drum application. So what we have here is we have set up a potentiometer as a variable voltage divider because we wanted to control the amount of filter output signal that we feed back into the ladder. And by doing that, we could control the amount of resonance that our filter has. And now for a filter, this makes total sense because, of course, you know, you're filtering your square wave and maybe you just want like a slight touch of resonance. And then you only like turn this potentiometer up slightly. And that way, you know, you can control just the amount of resonance on the sound. But in our case, we are only going to use the filter in its self-oscillating mode. So we basically just need to set this to full blast, and then we're done. But if we are always going to use this at full blast, we can just delete this potentiometer here completely, because of course we are not using it. So what I did is I just took that away. Whoops. I just took that away, and then I just connected it like this. And now this this feedback amp always gets the full signal. But because this might be a bit boring just tonally, I also decided to mess with the resistance here. And the idea here is that, oh wait, maybe I'm just going to show you first that this still works in the simulation. So, yes. So what you're seeing down here is the signal that I'm picking up from the circuit's output. And as you can see, even though I took away all this stuff, the filter is still oscillating happily. And yeah, like I said, this is great. But one more thing that we can kind of tweak is, like I said, is whoops, this is annoying, is this resistance up here. If we tweak this resistance, we can actually kind of change the characteristic of our resonance, of our self-oscillation behavior. Because I don't know if you can see this, maybe if I drop the frequency bit down. Yes. So if you look at the oscilloscope down here, you can see that the waveform it's putting out is actually not a not a very good sine wave. It's actually a bit distorted. So it has like this weird, it looks a bit drunk, I would say. Looks like the sine waves that I draw. And this is basically due to the fact that the gain of this feedback stage is just a little bit too high. It just starts driving these diodes a bit so that this oscillation gets distorted. Okay, so what can we do? It's very simple. We can decrease the gain of this resonance stage if we increase the resonance up here. And just increasing it would be boring, because I mean just replacing the resistor would be boring, which is why I decided to just put a potentiometer here. So what we can do is we can take a potentiometer, we can put it, oops, this is super weird. Okay. We can put a potentiometer in here. We can choose a sensible value, which in what I've tested was 20K, seemed to work quite nicely. Then I would drop this one down to 10K. So now, in the most extreme case, if you set this potentiometer to the full 20 kilo ohms, then the resistance here will be 20 plus 10 kilo ohms, so 30 kilo ohms. And in the other most extreme case, you would drop this down to 0 ohms, and then you would just have 10 kilo ohms here. So let's take a look at what that does. Okay, so as you can see right now, I've really turned this potentiometer up. So this is now 20 kilo ohms. This is 10 kilo ohms. So this entire pathway is 30 kilo ohms. And as you can see, the resonance looks much more like a proper sine wave. Looks much rounder, looks less drunk, just, you know, overall looks like a better shape. And now watch what happens as I decrease the resistance here. Okay, so first of all, signal is getting louder, of course. But then also, you can see how it gets progressively bent. And actually, kind of starts looking like a filtered square wave, which is interesting. But yeah, now if I drop it back down again, you can see how the distortion kind of goes away. And then you have, at some point, you have a decently okay sine wave again. Somewhere here, yeah, right at the end. Okay, and I just thought that might lead to some interesting, leads to some kind of interesting distortion, which I like in moderation. I like it on a kick drum sound, which is why I put this in. Okay, and I will just show you how this sounds on the actual circuit bit, because I've already built this, because I wanted to spare you the torture of sitting through watching me, build this on a breadboard. So I will switch over to the breadboard view, and I hope you can see the breadboard. Please talk to me. I can read the comments now again. Well, I'm just gonna pretend that you can see. Okay. So here is the oscillation, and right now, like, this is the potentiometer that I just showed you. Like, this is the one that I've implemented that that controls the distortion, on the resonance. So watch what happens as I turn this up. Now, interestingly, also the pitch drops, which I'm not entirely sure why that is, but let me turn this down a bit. But yeah, the pitch drops for whatever reason. And you can hear it sounds very, very harsh, noisy. Okay, let me drop it down again. And now it's kind of mellow again. And I will also show you what it sounds like when we use it to make a drum. Okay. Now it gets really dirty. And you can hear, like, when it's trailing off, you can hear, like, the individual clicks. So, yeah. Drop it down again. I think a bit of distortion actually sounds quite nice. Like, it has, like, a more aggressive kind of tone. So. And now if I turn it down again, it's clean and nice and everything. Okay, so now that we have that out of the way, let's get to the actual meat and potatoes of this stream, which is, like I said earlier, multiple times, we are going to cut out the external envelope. And let me turn this down. So first of all, let's get rid of this input here. And now we are back to manual control. Okay. So, building an envelope. For this, we are going to switch back to the circuit simulator. And I am going to open a new tab here. And now we should think about basically the easiest way to get this kind of voltage curve that we need to get our drum sound. And I don't know about you, but when I look at the envelope shape that I showed you earlier, with this spike in the beginning and then this drop off and then this slow trail off, actually the first thing that I think of is high pass filters, because if you look at what a square wave looks like when you put it through a high pass filter, it kind of has like the basic kind of similar shape. So I'm going to simulate this here by first creating, oh, that's the wrong one. I'm going to start by first creating a waveform generator basically. I'm going to turn this into a square. And I am going to give this a DC offset, because normally, like when you create a square wave here, it's going to be centered around 0 volts, but I would like to have it so that it's basically jumping between 5 volts and 0 volts for reasons that I'm going to get into soon. Okay, so like I said, I mean, this is just a basic square wave. So what happens if we just take like a very basic RC high pass filter, which is, as most of you hopefully know, is really just a capacitor where you feed the signal into, and then what you do is you take a resistor and you connect it to ground, and then we can just look at the signal that we get on this side of the filter. So in this window you can see the input signal, obviously, and in this window you can see the output signal. And like I said, I think you can kind of see the resemblance to the shape that we need. Now obviously, if I stop this, you can see that it's not quite what we need, because of course it has the quick attack, like it instantly jumps up, which is great, but then the trail off is kind of, it's kind of slow, because it takes a while until it gets to like the lower third, and then also the problem is that it doesn't stay there. It just it just dies off. It's just like this curve, and then it ends. But this is, I would say, this is actually not like a bad starting point. But there is actually another problem, which you might have already spotted. Like there's first this high spike, and then there's this low spike, which, if you're confused about how that works, now you can kind of see it here. Like whenever the signal here goes high, then of course it pushes current into the capacitor, and the capacitor basically, like the other side of the capacitor basically gets kind of, this is the wrong word, but it kind of discharges through the resistor and it pushes to ground. So then this side is charged, this left side is charged of the capacitor, and this right side is basically it's not at a lower level, it's at ground level basically. And then the problem is what happens if the input signal swings low, then the voltage on this side kind of suddenly disappears. And then because there was kind of an equilibrium before between these two sides, then like when the voltage on this side disappears, then the situation here is now like a kind of under pressure. Like I've explained this a few times in my videos, and this is like kind of how I think about it. It's like if you take the water analogy, it's like you push water into the balloon, and the balloon squeezes into this area, and it squeezes all the water that was previously in this area out of this area through the resistor to ground. And then when you drop the pressure from this side again, then what happens is that there's an under pressure here, obviously, because the whole equilibrium situation depended on the fact that you had a pressure coming from the left side. And so that once this pressure here disappears, you have this under pressure here, which you can see here clearly in this negative spike, which you can see, boom, it goes low, and then it pulls up current from ground to kind of refill this space, and that's why this negative spike then also trails off and goes positive again. And this obviously is a problem because that's not what we want. But still, I'm going to just demonstrate how this sounds, because I tried this already, I have to confess, and I think it just sounds neat because you can actually hear like how this sounds. So let me switch back to the breadboard view. So what I'm going to do now is I'm going to take this capacitor, which is a 10 microfarad, pretty big, and I'm just going to set this up like this. And then, since we don't want to use any external signal or modules yet, what I am going to do is I'm going to use a simple push button. So this is a kind of momentary switch. Basically, what this does is you can push this button, and then it will make contact between these two legs. What I'm going to do is I'm just going to use this to connect this side of the capacitor to the positive rail. Okay, so now basically whenever I push the button, the capacitor is connected to the positive rail. Basically it gets charged up. But like we saw in the simulation, what we need to do is we need to provide a path to ground on this side so that this actually works as a high-pass filter. So in the simulation I was using a 1 microfarad capacitor and a 1K resistor, but I think those values don't give you a good sound. So I think what I used was a 10K resistor and a 10 microfarad capacitor. So let's just try it out and see what happens. Okay, and now what I'm going to do is I'm just going to connect this other side of the capacitor to our CV input, if I can find a jumper. Okay, it's not beautiful, but hopefully it's going to work. Okay, so let's first verify that it actually still makes a sound. Yes. Perfect. This damn. Yes, Jonas, of course it needs to be buffered. This is like I'm just demonstrating like it in the most simple form. So I mean, you would think that we would now get our kind of kick-like sound, but you will hear that it's actually not the case, because yeah, this is weird. Like, why is it descending? Okay, so I can actually tell you why this doesn't work. Well, the problem is, if we go back to the simulation, what we have here, like what you can see here, is that our capacitor gets charged by the incoming signal. You know, like whenever the incoming signal goes high, the capacitor gets charged. But also, if I turn up the speed of the current here, you can see the capacitor gets charged in this direction, but it also gets discharged into the signal. Like whenever the signal goes down to ground, then the capacitor can discharge from this side, because of course there is a charge in the on the capacitor here. And in what I have built here on the breadboard, since I've used this momentary switch, whenever I let go of the button, it will just kill the connection, and it doesn't provide a path to ground. So our capacitor can't actually discharge, which is kind of unfortunate, which is why what we have to do is we take another 10K resistor and we just plug it in here. And now, because I'm kind of obsessed with order, I am going to use a jumper to make this nice and tidy. Okay, so let's see what happens now. Okay, it's not bad, but as you can hear, it's weird because the sound dies as soon as I take away my finger. So as soon as I stop pressing the button, the sound dies. Also, you will hear that on repeating presses, the pitch actually goes down. And also, if I keep my finger on the button, then you get the full, discharging thing. But I mean, yeah, this has multiple reasons, and someone wrote in the chat, like, don't we need to buffer this? Yes, we absolutely need to buffer this, because the problem is that right now we are not controlling the way that this capacitor is charged and discharged in any way. Like, we're just providing a path to ground here. We are providing a path to ground here, but of course the capacitor will also discharge into our filter CV input, because like I said earlier, this CV input is just a voltage divider. So what happens is that current will flow from the capacitor into this voltage divider and from here into ground. So effectively, on this side of the capacitor, we have two separate ways that our capacitor can discharge through. And of course, this will completely mess with this discharging curve. And then also another problem is that the 10K that I used here, and I'm not sure if it even is a 10K. Let me check. Yeah, I think so. The problem is that this does not allow our capacitor to discharge fast enough. So we get this weird, change in pitch. And also, if I turn the cutoff frequency up manually, and then I do this, you can actually hear exactly what we saw on the simulation. Like, first, the pitch drops down, and then when I let go, we have the negative spike. So it just goes down and whoop, goes up again. Which is kind of neat, but obviously it's not what we're looking for. Okay. So what can we do here? Well, simple. Lately I have been using a lot of diodes, so let's continue in this manner. Well, first of all, let's kind of adjust the values here to reflect what we actually have. But this is probably going to look very boring because, yeah, of course, like 40 Hertz is of course way faster than I can click on this button, so it's going to look off here. So let's drop the values down again. It's not that important anyway. Okay, we go down to a 1K here. Okay, so first things first, what can we do about this negative spike? Well, we can use a diode. Because of course, if we take a diode and we put it right here, and then we put our output here, whoops, you see it doesn't work. Why does it not work? Well, there's actually no current flowing through the diode because our output is not, it's not pulling any current. So the diode is actually not working. So what we need to do, here in this scenario, just in the simulation, what we need to do is we need to put in a resistor to ground, and then what we will see is we see the positive spike, and whoops, we also see a negative spike, you might think. But if I stop this, you can see that this is actually like an extremely minuscule voltage. It's minus 170 microvolts, which if I'm correctly informed, correct me if I'm wrong, it's just like that a diode is of course, like, it's not perfect, it can't block perfectly, so there's always going to be some leakage, I think it's called, but it's such a small amount that it's I think negligible. But yeah, if we do this, then we can actually cut off this negative spike, which is great. Okay, so I will switch back to the. Oh shit! I wasn't in the simulator. I'm sorry. Okay, so now you should see the simulator. I will show it to you again. So what I've just done is I've put in this diode. I've put in this resistor just for current to be able to flow through the diode. And then what we see here is we see first the positive spike, and then we see this negative kind of dip. But as I've shown you, this is just a very minor dip. It's in the microvolts, and I think it's negligible. Okay, so what I will do next is I will go back to the breadboard, and I will take another diode, and I will check on the chat for a second. Yeah, you see the breadboard, I'm sorry. Okay. Are you also considering the forward voltage of a real diode? You mean now for the for the part here? Well, I mean, yeah, of course. For now, like I said, we're just spitballing, so the actual voltage that we get is not that important. But of course, yeah, I mean, in this scenario, this diode that I put in here is going to lower the voltage here. So on the breadboard, my switch here is connected to plus 12 volts, so we won't have 12 volts here as a spike, but something below that. But for now, this is not very important actually. Okay, switch back to the breadboard. So what I will do now is I will replace this jumper with a diode. Okay, now I need to find a jumper that fits in there. Maybe this one will do. Just barely, okay. Okay, so same procedure. Let's look at what happens now. I will push the button. And yeah, no negative spike. Just a positive. And if I drop the cutoff knob, if I drop it down, we get something that sounds, I mean, like when it's very low frequency, it goes kind of in the direction of a drum. But yeah, as you can tell, the problem is really just that this is not very good, because we get these pitch shifts in the frequency. So what I'm going to try and do is I'm going to take this 10K resistor here that allows our capacitor to discharge on this side. I will just try to replace it with a 1K and just see what happens. Okay, let's see. It's not much better actually. Now this got me wondering why the pitch is actually going down. I think this is actually a wrong value. Let me check. I think this might be 47K, and that might be the reason why we get these strange pitch shifts. Okay, I will check. And yes, it's actually 47K. That explains a lot. Okay. I'm very sorry. Let's change this to a 10K. So here, 10K, let's see. Plug this in and let's see. Well, I mean two things. First of all, the pitch shift is still there if I push very quickly, because this, I mean, right now off the top of my head, I can't exactly explain why the pitch shift occurs, but it definitely has to do with the charging state of the capacitor. You know, if it's how full it is when you push the button, because I think if the capacitor still has some charge in there and you push the button again, then actually the size of the spike that we'll be able to pass through will be smaller, and that's why you get the lower pitch there. And oh yes, this is just an audio output. It's very boring. Actually, I don't send any CV in here right now. I just use this button to kind of trigger the drum, basically. Okay, so as I was just explaining, I think that the problem is like if the capacitor is still kind of charged when I push the button, then the size of the spike is going to be smaller, and that's why we get this kind of descent in pitch. And also you're going to notice that now, like the sound is much shorter lived. Yes, Mike, I had a resistor to ground after the diode, but this was just because in the simulation we didn't have any path for the capacitor to discharge through. Like we needed something. I mean, yes, like we didn't have any path after the diode for where the current could go. But in this scenario, we have the CV input, and our capacitor can basically discharge into the CV input. Dankeschön, Lena. And yes, so in this scenario, we don't need the resistor to ground after the diode. So because you know it can discharge. But what I was saying is the problem is right now the sound is very quick and short-lived. You know, which I mean maybe in some scenarios you can use this as like a kind of zapper sound or something. But in our case, we want to make a drum, so this doesn't work that well. So as you saw, like what we could theoretically do, of course, is we could increase the value of this resistor. Like if we increase the value of this resistor, then it will take longer for the capacitor to discharge, and then the sound will go on for longer. So I can just show you again. So I'm going to take this 100K, no, 47K, sorry. Just going to drop this in here. And now we have a much longer sound, but like I said, if you press repeatedly, the problem is the capacitor is still charged and it won't, you know, properly trigger again, which is a shame. So obviously this is not ideal. So we need to think about alternatives. So let's go back to the simulation view. So someone said this before. So the problem is we basically need to work on isolating the capacitor. You know, because the capacitor should be able to charge and discharge like independently of anything else. So we should kind of create a situation where the capacitor is only drained through one resistor that we set. Like there shouldn't be anything else influencing the discharging process. And right now, the problem is that we have this resistance, which is influencing the discharging process. But I mean, in the simulation, we have this other resistor, which is also influencing the process. In our circuit, we also have the CV input of our filter, which is also draining the capacitor. So there's multiple variables basically at play that influence the discharging process, which is a bad idea. And also, we should try to make sure that the capacitor is always empty when we re-trigger it, or you know, as empty as possible. And so someone suggested this already. Like the first thing that we should definitely try and do is we should try and buffer the output to make sure that there's that we get rid of this additional path through which the capacitor can be drained. So if I just take an op amp and I just set it up like as a very, very basic buffer like this, then you will notice that this won't work, because like we saw before, the diode, like there needs to be a current flowing through the diode so that the diode can work. So we actually need to have an additional resistance here, but the good thing is we can clearly define it. And if we pick a really big resistance here, let's say 100K, then in effect, it's not going to, whoops, we need another output. So if we choose a really big resistor here, then the amount of current that flows through this resistor is going to be like extremely small. And so it's, I mean, of course it's going to affect the charging, discharging of the capacitor, but just so, what's the word? It's not going to be significant, like you're not going to basically notice this. Okay, so like this, we should be a bit more in control of the speed of the discharging process, because now what we could do is we could make this resistor here into a variable resistor. So of course we're going to use a potentiometer here, but sometimes in the simulation it's just easier to implement a slider for this resistor. So what I can do now is I can increase the resistance here, and then you can see how the curve changes. And now we have basically control over the curve, which is not a bad idea. And also what we can do now is we can drop down the value of this capacitor. And what this is going to do in the long run is, if our capacitor is of a smaller value, then we have less charge to get rid of once the capacitor is charged. I mean, this is not going to help us right now, but in the long run this will help us. So this is what I'm going to do. I'm going to drop down the value because then it's easier to drain it, basically. Okay, so first of all, let me set this up on the breadboard. So I'm just going to rip all of this out, which, by the way, is always like if you're ever building something on a breadboard and it doesn't work, like something's completely off. Just in my experience, oftentimes it's much more efficient to just tear everything down and just rebuild it from scratch, because often like you're not going to find your mistake. And for some miraculous reason, it's going to work afterwards. Okay, let me get out a op amp, which I guess you like everyone, like if you are in the situation that you're trying to build components right now, I'm pretty sure that you've had the problem that you can't buy any op amps, which is super annoying, like this semiconductor shortage. I've managed to like nab the last TL074s from my local store. Like I got lucky, but yeah, I mean it's the same with potentiometers and all this stuff. Like I recently ordered some alpha pots, and I had to order them from Thonk. And I had to pay like all this, import tax because of Brexit, just because I couldn't get them anywhere else. It's crazy, actually. But yes, okay. So let me set up this op amp. I'm always like really terrified of connecting my op amps with the wrong polarity, even though like I know by heart like which connector is which, but I'm still terrified because I mean you're going to just smoke them instantly if you connect them the wrong way. Okay. And now I have to take a look at the simulation again because I don't have object permanence, apparently. Okay, so I am going to use a 100 nanofarad capacitor. I'm going to set this up here, and just like before, I'm going to take my momentary switch and I'm going to connect this side to the positive rail. Okay, and then like before, what we also need to do is we need to provide a path for the cap to discharge through on this side, which is why I am going to reuse this 1K. I really hate this. Like I have so many jumpers. Like I've bought like 4 packs of these, you know, of these jumper sets, and that should be plenty of jumpers, but for some reason I just lose them. Okay, so now the capacitor can discharge. We have that. And then what we need is we need a path after, like on the other side of the capacitor, like we need to discharge it there. So what I'm going to do is I'm going to use another potentiometer. Oh wait, can you? I think you can't see my breadboard. I'm sorry, hard to keep track of this. Okay, so just what I've done is I've implemented this this capacitor. I put in this switch. I put in this resistor to ground. And now what I'm going to do is I'm going to use a potentiometer to connect this side of the capacitor to ground. And then what we can do is we can vary the resistance to ground, and by that we can influence like how quickly or slowly the capacitor will discharge. Okay, so now we have a situation where we can basically charge this capacitor instantly, and then with this potentiometer we can set the time it takes for the capacitor to discharge. And now what I will do is I will use the diode to connect our capacitor to the to an op amp buffer. And I would just set it up as a straight buffer for now. Yeah, like it's actually it's super annoying that it's taking so long. But like I was surprised, like when I ordered from Thong, it actually took I mean, I think that they're like operating at a, what's the word, lower capacity at the moment, and I was sure it's going to take a month or two, but actually it came after 2 weeks, so I actually can't complain. Okay, so now we have buffered our output. I need to put in the resistor to ground also. And I think someone commented why I don't put the diode after the op-amp's output. Actually, good idea. For some reason, I haven't thought of that. And after I tried this, we can try that and see if this changes things. Okay, so this is set up now, and just because I wanted to go a bit more quickly, I'm not going to be super neat with my wiring. I'm going to cheat and just take a longer wire and kind of abuse it. Sorry. Okay, not pretty, but should work. Let's see. Well. That's not very promising. Okay, something's obviously going wrong here. Well, I didn't miswire the op-amp at least. I think it might actually be, like, the problem might actually be that the cap is too small, you know, to get a voltage curve that's actually audible. So what I will just do is I will just replace this again with the 10 microfarad. And let's try this again. Same result. No. Haha. Okay, so here you can hear something. Still have the pitch drop because the cap is so big. And yeah, no, it's there, it doesn't work. But the sizes are just not well chosen, I guess. Okay, so let's use a bigger potentiometer, I would say. I will bring out the big guns and we will use a 1 megohm. Okay, let's see. Okay, so now if I turn this up. Okay, so obviously now the problem is that if I turn the pot up just slightly, then the resistance to ground is so big that the capacitor will discharge so slowly that you know, we won't be able to trigger it again. So now I'm going to exchange this for a 100 nanofarad again. Okay, let's go. Yeah. No, it's obviously maybe wait a second. Maybe we also have to increase this resistance here. You know, because right now this is just a 1K, and so the cap can discharge like very quickly on this side. Maybe it's doing something. Let's just try it out. think that actually the capacitor size is just the bottleneck here. So it's just not going to work with a 100 nanofarad, at least not in this application. Okay, so we were there already. Yes, but this, I mean, it works in a way, but the pots in the stream, you mean these potentiometers? The guys in my shop call them Z-Achse, Zahnachse. Not entirely sure. I don't think that's the official name, but it's like a very, very basic kind of potentiometer that are available, I think, widely. Sorry. But yeah, obviously this is not gonna get us very far because we have multiple problems, and I think the most glaring issue is just the re-triggerability, if you want. So let's go back to the drawing board and think of something better. Okay, so this time I remember to switch the view. Okay, so as we have discovered, these values are not going to work, and this is basically for the reason that this capacitor's charging state basically determines how soon it can be re-triggered again, and this is also basically tied to the fact that we are pushing a lot of charge into our capacitor. So whenever I push the button, like relatively, I push it like for a very long time. So I really charge up the capacitor, and this makes it difficult to kind of get it to discharge in time. So what I think I will try to do is I will not use this capacitor here to create the envelope. What I think I'm going to do is I'm going to try and use this capacitor just as a pure gate to trigger converter. So this is basically what you can see here. Like it turns a gate signal, which is just a signal that's on for a longer period of time, and then it switches off. It transforms that into a quick spike. But you can see here that I mean, our spike still has this this curved shape, and like if you will, like a real trigger would just be an on-off signal that's instant and that doesn't have that curve. So what I am going to do, this will sound familiar if you've seen my latest video, is I will turn this op-amp from a buffer into a comparator. And what a comparator does is a comparator basically looks at its input signal. So in our case, that would be this spike here. So the comparator looks at this spike, and then what it does, like you can set a threshold for a comparator. Like you can tell it a threshold voltage, and the comparator will look at the input signal and it will measure that against the threshold. So in our case, we can see the signal jumps up to around 5 volts, like a bit below 5 volts. And so if we were to set a threshold at 4 volts, let's say, then what we could do is whenever the input signal, so this spike, passes this 4 volt threshold, then the output will go high, and once it crosses the threshold again on the way down, the output will go low. And let me set. This is always important. They set the supply voltage for your op amps to plus or minus 15 volts automatically. So we should just drop it down. Okay, and that's what a comparator does. And using that, you can basically turn this curved shape into a just very quick on-off spike. And getting this done is actually extremely easy. We just have to get rid of this feedback path. And instead, what we are going to do is we are going to use a potentiometer. Oops, no, not like that. We're going to use it like this. And we're going to set this potentiometer up as a voltage divider. So we are going to feed it our 12 volts on this side, and we're going to connect it to ground on this side, and then we're going to feed this into the inverting input. And what that does is that will configure this op-amp as a comparator, and whatever voltage we set here will be the voltage that the comparator compares the input signal, so our spike to. And you are going to see that this right now results in nothing, because the problem is, like, right now I've set the threshold voltage to 6 volts, and of course 6 volts is higher than our spike is, because we saw that our spike is just at 4.6 volts. Sorry. And so since the threshold is now above the spike, the output is always going to be low, because remember, the comparator, the output of the comparator is only going to go high if the input signal is above the threshold. Threshold is 6 volts, spike is 4.6 volts, so it's below the threshold, so it's always going to be, the output is always going to be low. But if I drop the voltage down, let's say we go to there, right? So now we're at 4.1 volts, roughly. And now on the output, we see this beautiful spike, which is extremely short, and it's just like, you know, a quick burst of voltage or current or whatever. No voltage in this scenario, which is great for our purposes, because now we can use this little thing, and we can use it to, like, instantly charge a capacitor and just, you know, push some current in, and then have it be able to just discharge instantly. So, oh, one more thing. You will have probably noticed that we have kind of a problem here. Like, we see that the resting voltage is at minus 12 volts, because a comparator can really only be in one of two states, which is either at the negative supply rail or the positive supply rail. And so you can see it jump from minus 12 to plus 12 volts here. And that is actually not ideal. Like, I would like to have the resting voltage at ground level, simply because it's just more in line with the CV, what the CV input expects of our filter module. So the CV input of our filter module is kind of what's the word? Kind of expects like 0 volts as a baseline. So what I'm going to do is I am just going to, this is kind of hacky, but I'm just going to connect the negative voltage input to ground instead of the negative rail. And then what happens is that the resting voltage is now at, well, it's actually a bit below ground for whatever reason in here. But yeah, this will kind of hackily turn this neutral level into a ground level. Okay. And so now what we can do is we can, at its most basic, what we can do is we can take a capacitor, we can put it in here, and then we can take a resistor and we can put it in between here. And now what happens is every time the comparator's output goes high, you know, when you have like this little spike, then it will push a current into the capacitor, charging it. And once the output goes low, then it's at ground level, and then the capacitor can basically just discharge into the output of the op-amp. And now we can tweak these values to kind of influence the curve. So you can see like we have like a very long trail off here, which is probably not ideal. So I'm just going to drop the value of this capacitor down a bit, and that looks a bit more like it. But we're going to have to check with this on the breadboard anyway. But this is what I'm going to try and do now. So I will, for our spike, I mean, it doesn't really matter. Oh no, it actually does matter. this is actually it's actually kind of the reason why I've did it this way, because now for our comparator, it doesn't really matter like how long the trail of our input spike is. So we can make this extremely short. Like say I'm going to put a 1K resistor here. So the spike is extremely short. So this capacitor will basically discharge almost instantly. And this means that we can hope that we don't have this retriggering problem, because now, you know, the current flows in and out at a much quicker pace than we can press the button, hopefully. Let's see. And this should help us with this retriggering problem. So okay, and obviously also one more thing that we should just do right away is we should buffer the output of this stage again. Oops, that's a bit cramped. Let's get this in here, and we'll connect this, and we'll connect that, and then we'll connect this like this, and then we can attach the output here. And we have our curve here. And also, of course, we should use a potentiometer here. Actually, I I would have just done something stupid, because I'm going to show you. Like, the problem is, if this resistance, like let's say we do this from 100 ohms to 10K. Okay, so as long as the, which one is it? Oh, so many sliders. So this is the right slider. So as long as this value is comparatively low, I'm going to delete this so you can get a better picture. So as long as this is just comparatively low, this is going to look like kind of like the shape that we want. But watch what happens as I increase this resistance. Actually, that's not what I expected. Weird. I kind of wait. Yes. Let me drop this down in this direction. Weird. That is weird. I mean, now you can see what I mean. Like, you can see that we get an attack here. If I stop this, we can see, you know, we don't have this instant rise anymore. Now we have like this angled rise, which is what I wanted to show. Because of course, if the capacitor is charged through here and we raise this resistance here, then charging the capacitor will take some time, because, you know, you have this resistance here, which kind of is in the way of the charging process. So obviously you're going to get an attack, which is not ideal. So we're going to have to do something about that. But right now I'm very, very irritated by the fact that this only jumps to 200 millivolts. What? Why? That's weird. Let's look at the output here. Okay. I mean, this is basically a ground level, and this only goes up to 500 millivolts. This is really weird. Okay, you guys have any idea what might be going on? Let me check the chat. Maybe it does below ground because. Okay. So I'm just going to keep guessing. So why could that be the case? Maybe if you raise the voltage here. Yes. Okay. Sure. So of course, like if the, yes, this makes sense. Okay, so let me just explain what happens. I'm going to try and show you. So we don't need the input signal. So what we need is, we need to look at the input spike, and then we also need to look at what the comparator is putting out. And then we also need to look at the output. I hope you can see all of this. Okay, so the situation that I just had was that this resistance, I pulled it down very low. So let's say we go down to 1K. Then you can see that the spike, the spike here, so the spike from the capacitor is very narrow. And that means that the spike that the comparator puts out is also very, very narrow. So, I mean, this kind of view here is very kind of slowed down, but this is an extremely short spike. And the problem is that that the spike is just not long enough to properly charge the capacitor, and that is why you can see here that the voltage is so low. That's why it's just 500 millivolts, because this short blast of voltage is basically not enough to properly charge this capacitor to a reasonable voltage level. So what I did is, if I increase this resistance here, if I increase this resistance over here, then you can see that this spike gets wider, and that means that it's over the threshold for longer, and this means that the blast that is coming out of the comparator is also long in duration, and that means that the capacitor can get charged to a reasonable level. Now we can obviously toy with this a bit if we change the value of this capacitor. I mean, right now it's a 1 microfarad, which is actually pretty big. If I drop this down to just 100 nanofarads, then we can see that now it's actually going up to a really decent value. It's actually going up to 10 volts, because of course a smaller capacitor will be charged up much quicker than like a big 1 microfarad one. So and by doing this, by dropping the value down, we are actually able to lower this resistance again, which as I explained, I want to do because I would like this capacitor to charge and discharge very quickly to allow for repeat pushes, basically, so that we can re-trigger the whole thing. Okay, and now we can basically go back to what I was just talking about, which is this resistance here. So as you can see, as I explained, we have this resistor which is connecting our capacitor and our comparator's output. So what this means is that the capacitor, of course, it discharges through this resistor, but it also charges through this resistor. And that means that since it now takes some time to fill up the cap, we get this attack. You see, it's not an instant rise. It's like this now slightly angled rise, which for our drum sound is not ideal. What can we do about that? Well, answer very simple. As so often, it's diodes. Because if we do this, if we just create an alternate pathway where we put a diode in this direction, then what happens is that the voltage spike from the comparator can just go through the diode and into the capacitor, just filling it up instantly. And then once this goes low, once it goes to ground, then the capacitor can discharge through the resistor. And this way we're going to ensure that we always have a quick attack, and then we can change this resistance value to get like a slower release, basically. Okay, let's see if it works. And yes, you see something weird here. You can see that there's like this plateau. We don't have this spiky behavior like over here, but we have this plateau. And this is due to the fact that our comparator, like the signal our comparator puts out, is actually high for a relatively long period of time, because I've dropped down the threshold voltage basically to ground. So what we need to do here is basically just increase that threshold voltage. So if I pull this up, that doesn't work at all anymore. Okay, let's drop it back down a bit. Let's drop it back down. Boom. There it is. Okay, now I need to find the sweet spot. No. So it seems like I have to maybe drop down this resistance over here to which one is which? Okay, drop this down, and then I will increase this voltage here. Okay, this is not good, I guess. I mean, we could just try and listen to it, but I would say this is not ideal. Maybe if I drop this resistance here down, does this affect it in any way? No, it doesn't. Okay, this is annoying. Changing this doesn't work, right? Does it do anything at all? Yeah, it kills it. That's it. This is weird. Maybe if we play with the capacitor size here and drop it down to a 10 nanofarad, this is probably only gonna. Oh no, it actually works. Okay. But I guess then we need to change the range of this guy. Let's push this up to a, what do I have, 20k? 20k for now. And then let's see what we can do here. If we increase this, it doesn't work anymore. Why does it not work anymore? There it is again. Okay. Push this up. Okay. So I'm beginning to suspect that the problem might be that we need an additional path to ground here, because right now, like whenever the output here is high, you're going to have this plateau situation here. There's no way for the current to go, so that's why it kind of will keep pushing into the cap, and it will keep pushing or holding the voltage up, which is not what we want. So what I will try to do is I will move all this stuff over here a bit. Boom. And then I will connect this here, and I will put in an additional path to ground. And I will raise, I will raise the voltage here. It doesn't really help, does it? I was actually expecting this to go better. Let's raise the value here. And we still have the plateau. Let's check the chat. Maybe someone had an idea. Did someone have an idea? Try setting threshold really high. The constant part of the pulse should equal the pulse width of the comparator. Don't quite know what you mean. Yes, it will be possible to watch this after it went live, but I will just put it on the Patreon, but for all the tiers. So even if you're the lowest tier, you can still watch the stream, basically. Okay, shorten the time constant of that input integrator. So you mean this here? This area? Sorry, I feel a bit klutzy right now. Okay, let's make this shorter. Let's drop the value here down and see if that does anything. That just kills it. No, but I mean, we can definitely say that this did not do us any favors, that this didn't work. I would just say, let's just try this and see how it sounds. I'm just curious. And then if it sounds bad, we can still we can still try something else. Okay, so I will switch over to the breadboard view. Okay. Good. I will try to translate this to the breadboard. Let me check with the schematic. Okay, so the first thing that I will need to do is I will need to exchange this capacitor for a smaller one, which thankfully is an easy thing to do. I'm going to go with a 100 nanofarad cap for now. And then we can get rid of the potentiometer here because we are not going to need a variable discharge speed for this capacitor basically. So we can take it easy and do something simple. I will use a 1K resistor to allow this cap to discharge. Maybe that's too low a value, we're going to see. And I'm going to match that value on the other side. Okay, so now we should have our spike coming from this capacitor. And then I think I can actually get rid of the diode, right? Because I mean, since we're using comparator, it only matters that that our spike goes above the threshold. So it doesn't matter if it dips into the negatives because the comparator doesn't care. Wait a second. No, it would. Okay, give me a second. I was going to. Yes, I mean, I wanted to do this hack where I connect the negative supply of the op amp directly to ground, but that might actually then not be a good idea, because if I feed a negative voltage into the op amp's input and the supply voltage sits at ground, I think this is unhealthy for the chip. So that's actually a bad idea. So I'm just going to keep the diode there, just to keep my chip healthy and chugging along. Whoops. Sorry. That's what you get for operating on a live circuit. Okay, so first of all, I will connect the negative supply of this op amp to ground. And we can keep the diode. We can keep the 100K resistor here. But what we need to change is we need to take out this jumper so that this op amp is no longer a buffer, since we want to turn this into a comparator. And now what I'm going to do is I'm going to take a potentiometer. I'm going to turn it into a variable voltage divider. Like this. Okay. So I'm trying not to cram the breadboard too much so you guys can actually see what's going on. Okay, put this in here. And now all we need to do is we need to connect the middle pin of this potentiometer to the op amp's inverting input, and by that we set the threshold for the comparator. And again, I'm not going to do this pretty because it's going to take too much time. I'm just going to wing it a bit. Okay, now the comparator is set up, and we should be able to push in our spike, and we should get the trigger signal from the comparator. And now what we need to do, if I switch back to the simulation, now what we need to do So all of this is now set up, and now we need to implement this part, and then we can connect that to, like we can connect this part to our CV input of the filter. Okay, so let's go back to the breadboard. So what I need to do is, first of all, I need to do this this thing where we use another potentiometer to send the pulse to our capacitor, and then the diode to provide this direct charging path for our capacitor to be charged through. It's actually crazy. I had 2 bags of 100 diodes. I bought them, I don't know, like a year back, and I thought I'm never going to run out of diodes. And the problem is that I've decided to make this filter into a Eurorack module, and I got a few PCBs and I started soldering. And then at some point I realized, fuck, I'm nearly out of diodes. Like I have maybe, I don't know, like 10, 15 diodes left, which is crazy. I don't know where they all are, but yeah, it happens. Okay, so diode here, then we need another potentiometer. I'm going to go for a, let's try 20K for now. Okay, let me switch back to the breadboard. Oh no, I'm already on the breadboard. Great. Yeah, I also realized that, like, it's strange in the simulator that it shows it's at 22 volts. I mean, I think it can happen in some scenarios, like when you build something that's kind of like a charge pump, but I don't know if that applies here. But yeah, okay. Let's try to get this set up. So I'm going to take the output, I'm going to move it over here just to have a bit more space to operate, because right like this it's a bit too cramped. Okay, so here what I'm going to do is I'm going to take another 100 nanofarad capacitor. And we know that one side needs to connect to the non-inverting input of the op-amp, and the other side needs to connect to ground. And sadly, it doesn't work like this, because the capacitor is actually too small to kind of bridge the gap between the middle part here and the ground rail. So I'll have to do it differently. So let's just put it in here. And then I will use another jumper to go to ground. Boom. And now what I need to do is I need to connect, the op-amp's output to this side of the capacitor through our diode. This was in order to quickly charge it. Okay, and then also we are going to use our potentiometer as a way to discharge it. So I'm going to put that over here. Oh yeah, you're also running out of diodes. It's really annoying. Am I going to add buttons for drumming? I mean, I think it would kind of be a novelty feature, no? Like, I mean, yeah, of course you could manually drum, but I mean, space on the front panel is already limited as is if you're using Eurorack. So I kind of doubt it. I mean, maybe build like a breakout module, you know, build a separate module where you just have like different control elements. Maybe you can implement like some kind of, you know, button module. It's just a bunch of different buttons. Or I was just thinking, I mean, there used to be these controllers for this game. I think it was on either N64 or Super Nintendo, like this Donkey Kong game where you where you play bongos. Maybe you could use those to trigger this. Might be cool. Okay, nearly done. Okay, so now we have the comparator going to the capacitor through our diode, so it's charging it. And then we have this alternate pathway through our potentiometer, which allows the capacitor to discharge into the output of the comparator. And now all it's left to do is we need to connect this left side of the capacitor to our non-inverting input of another buffer. And then from there we can finally go to our CV input. Okay, nearly there. So now I'm going to connect the buffer's output to our CV input on the other side. And then we're going to see if we hear the plateau or not, and we're going to see how this sounds. And yes, I guess you hear, I guess most of you know, I live in Berlin, and I live like in a very central location, which on the one hand is nice because, of course, like it's close to everything, and public transportation is very good here. But the downside is there's a lot of crazy people in front of my window, and just people like revving their engines, like showing off in their fat cars. And then there's a lot of crazy people just like screaming at night, like at 3 a.m. So I wouldn't exactly recommend, I would say. Okay, so I kind of have an uneasy feeling because I've just winged this so much, but let's just turn this on and let's see what happens. Well, at least it still oscillates. Okay, so it seems like this is actually constantly at a high voltage. And it doesn't work. Okay. Let's turn this off before anything goes up in smoke. And let's think about what I might have done wrong. So let's re-examine this. So we have our capacitor here. We have our switch here. And with the switch, we charge the capacitor. Then on this side, we have a 1K that's going to ground, and this allows the capacitor to discharge on this side. So whenever we charge it up and we release the button, then basically the cap can go through this resistor to ground and discharge. Okay, so this seems fine. Then on the other side, of course, we have the same kind of resistor to ground that allows the capacitor to charge and discharge on the other side, you know, always in the inverse direction as what is happening on this side basically. So this also seems okay to me. Then we have our diode, which is going to the non-inverting input of this op amp, which seems okay. Here we have our 100K to ground, which does not strike me as being a problem. Okay, and then we have our comparator, our comparator's voltage here. And now I have to think, is this positive, is this negative? I think this is actually the positive rail. Okay, so this should be okay. So what this pot then does is it allows us to set any voltage between ground and 12 volts. So this should be what we want. We are sending this into the inverting input, which should also be fine. It looks like this doesn't properly connect. Maybe that's already the problem. Not sure. Push this in here. Push this guy in there. Okay, so now this should hopefully connect. And then on this side, we use the diode to connect the op-amp's output to our capacitor. So this seems to be okay, I would say. And then on this side, we also need this connection to ground for our capacitor to discharge through. Now I'm wondering, did I put that in? No, of course I did not. So you can see I'm stupid. I kind of omitted the connection to ground here. So this potentiometer just didn't do anything. So let's fix that. So I will take a jumper. Oh no, actually it doesn't. It actually doesn't go to ground. It doesn't actually go to ground. Okay. It does. Of course, it doesn't. It doesn't go to ground. It goes back to the op-amp's output. Of course. So I'm not stupid. Sorry, past me. So this is actually correct. So what we're doing here is we are providing an additional path for the capacitor to discharge through, which basically, like, this red jumper is going to this leg of the potentiometer, and then the middle leg is leading back to the output of this op amp, which should be fine. It actually does look okay. Okay. Now this is really stupid. Okay, so you see here this jumper. So I've connected this side, this right side of the cap to the input, and of course this side is grounded. So I just sent ground in here, which is not a good idea. So what we need to do is we need to connect the other side to the non-inverting input. Okay, so I will push this guy in here. And now this is getting really, really crowded. Oh well. I mean, in my regular videos, you see that normally I care about my breadboard layouts, but right now, I really can't be asked. I'm sorry. Okay, so now we connected the correct side. Of our capacitor to the buffer, and then what we do is we send the output of this buffer to our CV input. Hopefully now this works. Let's see. Okay, at least no high-pitched whining. Yeah, this seems much better. Fingers are too mushy for breadboarding. Yeah, I can relate. That's actually why I bought these tweezers. I mean, it's nothing special, but I think this actually really helps because you can be just much more precise, and I just like this. I always reach for this. But yeah, time to celebrate. This actually sounds like it could maybe work. Let's see. Okay, so you hear a faint clicking noise, I guess. Okay, it's better than what we had before. Okay, so let me change the threshold first. Let's see what happens. Well, okay, so if we drop the threshold right down, then apparently this causes our comparator just to swing high. But then if I drop it down, if I raise it up again a bit again, you can hear that there's actually something happening. So let's increase this resistance here. It was already at the maximum setting. Okay, so this means that this resistance is just not high enough. And we used a 20K, which of course is like really measly. So I'm going to replace this, because why not go from one extreme to the other extreme? Let's replace this with a 1 mega ohm and see what happens. Okay, I've set this to the maximum value. Okay, so this really does not sound like a drum. Let's drop it down. Whoops. Something is very funky here. Ooh. Almost sounds like sample and hold. I'm not sure if this sounds healthy. I guess not. Jesus. I think it's because of the diode drop. I'm not sure about that actually. This is very underwhelming. Oh man. Okay, so it might actually. I'm thinking that maybe. Oops, I dropped this down. Sorry. I'm thinking that maybe we should not. Thinking that maybe we should just not use the op amp with, ground as a negative voltage. I mean, I know that there's like this. You have like what are they called? Like single rail op amps, and this is a TL074. So maybe it just doesn't like this. I don't know. Let's just go back to the way things were. So we are going to go back to the negative voltage here. You have a technical question. What reasons for choosing different types of capacitors except for the different ranges? With types, you mean ceramic or foil or electrolytic, I presume. Well, it's I mean I would say the main thing is polarity. Not polarity, like if they're polarized or not, because with electrolytic capacitors they are polarized, so one side should only ever be positive in relation to the other side. So if that reverses, like if you put in a electrolytic capacitor the wrong way, basically, then it can actually I don't know if it can explode under reverse polarity. Probably, they just really don't like this. You should never use an electrolytic capacitor in a situation where both sides might go positive or negative, so that's always a bad idea. Okay, Christian, use a diode after the op amp to get rid of the negative. Yes, that's what I was thinking. So now I've went again for the op amp to go with the negative supply voltage. So what you said is probably a good idea. Let me just switch back to the simulation for a second here, just because it makes it easier for me to think. Because just honestly, doing this alone in my room without anyone watching can already be stressful, because oftentimes you just don't know how to fix things. But of course, with people watching, it's just on an entirely different level. So I'm just trying to remain calm. But okay, let's go back to the simulation. I hope that you can see. And the first thing that I will do is I will now go back to the proper configuration here. And well, what we can immediately see is that the output of this op amp is going negative, which is not something that we want. But I guess you are correct. Like if we simply go to this op amp and we put a diode in here, and of course we need to put in a resistor here because otherwise it's just not going to work as we saw earlier. Then yes, now we get, I mean we still have the plateau, which is kind of weird, but we only get the positive voltages. But we also see that the trade-off is now very it's now very, very steep. So I guess we should increase the range on this resistance here. Let's go up to 100k. Let's not go so crazy as we did on the breadboard. So if I increase this, okay, now we have this massive plateau. Maybe we can reduce it by changing the threshold. This is really finicky, actually. Okay, so maybe if we raise this resistance a bit, it just makes it worse. You guys have any ideas? Let me check the comments. What's the minimum peak-to-peak voltage of a TL074? You mean supply voltage? I actually have never looked it up. What else? We are entertained. That's great to hear. Yes, I'm just panicking. Try putting the diode in the feedback path. Try putting the diode in the, you mean of the first op amp or of the second op amp? I would not call 4 milliseconds massive. You mean the plateau? Yeah, probably you're right. Probably you're right. Seems clipping. Yes, that's also true. Bypass first op amp to second input op amp. I look at the simulation and understand nothing, and you're asking me for ideas. They need labels. You mean the sliders, right? Yeah, I agree. They definitely need labels. So let's actually add labels here. So we will call this the release. I'm going to put this in caps so that it's screaming at us, so that we don't overlook it. And then we will call this the threshold voltage. And then we will call, I mean, this one, I really don't think we should actually be varying this. I don't think we actually have to. So I'm going to take this out. I'm just going to set this to a, I don't know, let's say 1K. And then we should have our spike here. And then this should actually be okay. Okay, so one thing that I'm thinking, maybe we can actually get around the whole problem with the negative spike if we simply do the following thing. I will simply not put this here. I will just simply not put this there. And I will just have the diode there. Take this out. And then I will move the diode down here. Whoops. Move it here. And now only the positive spike will go through, of course. So we don't have to worry about the negative thing. How can I turn this? Just going to delete this. And then I am going to use a resistor here. And then we can implement a slider here. So we'll basically turn this into a potentiometer. And Yeah, now it doesn't go negative, obviously, because the negative voltage is blocked. And with this resistor, we can control the trade-off. And then with the threshold, we should be able to influence the plateau a bit. Yeah, not much luck, but I think this might actually work, and I think it's actually a bit easier probably to do. Okay, so let me switch back to the breadboard view, and I will also check the comments. What did you say? Put the diode straight into the buffer input, but with a pull-down resistor, then you can feed it without complex interactions. Put the diode straight in the buffer input. Not sure what you mean. Can film or ceramic be subbed in for each other in most applications? I mean, generally, yes. Of course, you can use ceramic, but like usually when I buy my components, I go to a shop here in Berlin, which is called Segor, which is just like a very old school, like little electronics shop, which I like to support because it's not one of the big chains. The thing is, they have everything basically. Like not everything. They have a lot of components. Like they have a very good. They stock just basically everything you need. But the problem is the guys working there. Like some of them can be. How do I put this in a diplomatic way? They can be hard to interact with. Like if you don't have your concept straight and if you don't know your terminology and everything, they might take pleasure in letting you know that you should be better informed, which can be kind of a downer. And in the beginning, when I went there and I bought my components, I actually asked them this question, like, should I use ceramic or should I use foil? And in their typical kind of condescending tone, they told me that no, you should never use ceramic for audio applications because apparently ceramic caps that can act as kind of like a microphone. Like if you tap them, if they vibrate, I think they can kind of pick up frequencies, and they basically put it into your circuit. I think this is one thing, and then I think the other problem was with linearity. I think this is like very spitballed. I think that foil film capacitors are just have better linearity, so they introduce less what's it called, THD, total harmonic distortion. And that's what I've been told, and that's why I always tell people, if you do audio stuff, go for foil, go for film. Ceramic are apparently they are better for decoupling. So if you do decoupling, you can go for ceramic, fine. But for audio stuff, like for the stuff that I do here, mostly it's a better idea to use film or foil. ESR difference as well. No idea what that means, but been in that position in the 80s, not pleasant at the electronics store. Yes, I mean it's just I don't know. Like I feel like it's such a niche hobby, you know, to be into electronics, and you would assume that people are like more welcoming, because like it just, for me in my position, it's like, okay, I'm into this niche thing, and I actually have the problem that there's not many people I can talk to about this hobby. And you would assume that when someone new approaches you and wants to get into your hobby, you should be, you know, encouraging them. But I don't know, like some people just don't want to do that. Like they just want to put stones in your way. But whatever, I'm not going to complain. Okay. Oh yeah, you said the video quality drops. Another thing that's very annoying about living in Germany, our internet connections are really bad. Like even if you pay a lot of money for a good connection, it's going to be bad, it's going to be shaky, it's going to be often disrupted, just gonna, you know, just drop out. So very sorry if the quality drops. But okay, let's try to implement what I just put into the simulation. So it's actually very easy. So we can, I mean, what we need to do is we need to reconnect the negative supply of our op-amp to the ground rail. To the negative rail. And then we already have the threshold set, which is fine. And then we already have the diode that's going to our capacitor, which is also fine. The only thing we need to change is we need to change how this capacitor works. So right now, this basically connects to the capacitor on the one end, and the other end right now is feeding back into the op-amp's output. But as you just saw, we don't want to do that because we don't want to have a negative voltage at this point, because of course now the comparator is going to swing negative. And so what I will do is I will take out this jumper. Oops. So that our potentiometer is no longer connecting to the op-amp's output. And then what I will do is I will take another jumper and I will put this in here. No, here, no, here. Okay, and now the capacitor is basically just connected to ground. So now what will happen is whenever the comparator's output goes high, it will basically push through the diode, it will charge the capacitor up, and then once this output goes low, so once the comparator drops down again, then the capacitor will be able to discharge through this. It's still a 1 mega ohm. I'm going to replace this with a 100K. So then this capacitor will be able to discharge through this potentiometer instead, which is connected to ground. So then the voltage here is never going to drop below ground level, and that should be it. I'm a bit worried because we just had like this very weird, noisy, weird sounding stuff. But let's see if it's still there. Okay, just remember, like, one thing to actually look out for whenever you do something like this. Right now I've put in the potentiometer here, which is going to ground, which, I mean, in 99% of the use cases it's going to be okay, but and I've made this mistake a few times. The problem is if we now turn this potentiometer all the way, like if we turn the resistance value all the way down, then we basically have a short to ground here, because the op-amp will push through here, it will push through the potentiometer, which is now set to 0 ohms, and will go straight to ground. So we have a short, and then you will see smoke, and then you will be very sorry. So I mean, now with my new power supply, it's probably not going to happen, but still, we don't want to risk this. So I'm going to not use a jumper here, but instead I'm going to use a 1K resistor. Oh, I mean, that sounds nice. That sounds like a good experience. I mean, also in the shop that I talked about, some of the guys there are super helpful. They're super nice, and you can approach them. Cool, nice. But I mean, there are exceptions, unfortunately. Okay, so put in the 1K here. So now even if I turn this potentiometer all the way down, like even if it's really at 0 volts, then we will still have the 1K here. And then we won't burn my room down here. Yes, Glenn. It's actually the right idea. Okay, now kind of get this in here, which is a bit, this is a bit cramped actually. No, this doesn't work. Okay, kind of a rat's nest, but okay. Now, moment of truth. Let's see what happens. Still oscillates, which is always good. Huh, I think that actually the connection here is kind of bad. Super weird. Okay, well, maybe it's gonna work. Let's see. Huh. Well, we do have the spike, but it's super, super short. It's not even a clave, it's just nothing. Okay, so let's turn this resistance here up. Still, same thing. Okay, so what I will do is I will exchange this capacitor here for a bigger one. So just to emphasize the effect, let's first go with our old pal, the 10 microfarad capacitor. Just to see, you know, if you really exaggerated, like, let's just see what happens. Okay. Nothing happens. I feel like these breadboards, I feel like these tie points, like at some point maybe it's just a cheap breadboard. It feels like they just kind of like get stuck. Like sometimes I put components in and then you can't pull them out because they're like weirdly lodged in there. It's just super weird. But yeah, it doesn't work. Why does it not work? Does it still oscillate? Yes, it still oscillates. Well, maybe, just maybe, the resistor values that I picked here are just too low, because remember, these are 1Ks. So maybe the spike that this cap produces is just way too short to charge up our capacitor. So let's take 10Ks and let's try the same thing. Yeah, I mean, breadboard troubles are always just so annoying. I've done, like in the past, I've done, like before Corona, I did a few workshops with people, like in person. And we, like I bought the stuff for everyone, and I think we were 10 people, and for 8 of them I bought like these regular breadboards, and then for the two others I had to buy others because the shop I was at was out of stock, so I had to buy other models, and they were like these annoying kinds that have the power rails split here. So the blue and the red line are going to be split here, and then what happens is that these two sections are basically isolated, and so these poor people who have never built a circuit in their life are sitting in my workshop, and they're trying their best to kind of recreate the circuit that I show them. It just doesn't work at all. And then after like an hour of head scratching, we're like, okay, so there's no power on this side. That's why it doesn't work. I don't know. This is just something that you don't think about. Okay, onto the 10Ks here. Maybe this works. Okay, just to reiterate, what I'm hoping to do is I'm hoping to get this spike to be a bit wider, and so that the blast that our comparator is putting out is also a bit wider, and so the capacitor has more time to charge, basically. So let's see. Okay, short time. Yeah. How would I say this sounds a bit better? Ha! You hear that? It's almost like the very beginning of a drum sound. Okay, so like I said, now my next move will be replace this one with a bigger cap. So maybe the 10 will be overkill, but I will try it. Ha! Haha, okay. Perfect. And now with this pot, I can actually shorten So that's actually much closer. And now what we can try is we can try playing with the threshold voltage, see what that does. Okay. Okay. Okay, so play with the resonance control. Haha. Let me turn up the volume. The problem is that it's still, I mean, I know that like with the classic 808, and I think also with the 606, you also have like this slight effect that if you trigger it repeatedly, it will get this effect that it's like, you know, it's going up in pitch a bit, but I think this might actually be a bit too much. So maybe, I think if we drop this one down, and maybe we go for a 1 microfarad instead, which I hopefully have here somewhere. Oh yes, here, perfect. This is such a mess. Okay, let's see if this fits. It's weird how you kind of like, you know, like these foil caps, like they have this set distance between their legs. In German, it's called Rastermaß. I don't know what the English word for that is, but you know, there's like these different values. You know, you have like Rastermaß 5, 3, whatever, and basically it tells you like how many holes on the breadboard it spans. And I feel like it's kind of like back in the day when I was playing with Legos. So at some point you kind of get a feeling for, you know, like which part fits in where, like how many holes it's going to take up, and then you get like this intuitive understanding. Okay, so I have to put the jumper here, of course, because this cap spans exactly 3 holes. So yeah, it's weird what like the stuff that you learn. Okay, so let's try it with a 1 microfarad. Well, that's obviously too short. Very short, but I mean, you hear it doesn't go up in pitch so much because of course the cap has enough time to discharge. So I would just try to experiment with like a little bit of more resistance on this pot. So this was 100K. Let's go maybe with a 250K. So here is the 250K. Plug this in here, and we of course have to turn this up. Okay, so I would say that the decay is okay. It's not perfect, but probably okay. So if we drop down, the threshold a bit, then the cap doesn't get charged that much. And I think now one thing that I might want to do is I might want to raise the resistor value at the input of my filter here, so that, you know, because right now the initial sound is maybe a bit too high pitched for my liking. I'm not exactly sure if that's the problem, but kind of sounds like that to me. So I think right now I have let me check what I have there. Also, if you're a beginner, I don't know if there's any beginners here in the chat, but like one tip would be always buy a multimeter. Like if you're starting out, I mean, of course, like it's $20 and you might think that you could live without it, but honestly, it doesn't work. You need a multimeter. It's going to save your life in so many situations. Okay, so the resistor here was actually a 200K, which is already quite high. So I will try to drop it down. Not drop it down, raise it up a bit. But I will have to pick up something else. Give me a second. Okay, we will try it with a 470K. And then we will see what that does. It's also something that I realized, like in the beginning, I think it's really hard to get the components into the breadboard, but at some point you just realize like you have to just like, just push them in a certain way, and then you actually don't need a lot of force. You can just, just plug it in. But I noticed that in the beginning it was always a nightmare, but now it's like you know exactly how to push. Okay, let's see. Well, that is very low pitched actually. Let's raise the threshold here. That's what I kind of feared would happen. I mean, it is there, but it's so low. It doesn't work anymore. Okay, so we can't actually go lower with the resistance here. So I think I will go back up to the 200K. I think I did actually prefer the bigger capacitor here, just because we had a longer trail off. Okay, and it doesn't work. Ah, there it is. I mean, you can hear the problem is really this wild varying in pitch. I can try to turn it up a bit, but I guess it's already quite loud, the bass. You can see, like, I'm kind of dissatisfied with this, that the pitch goes up so much. Like, if it just went up like a bit, I think I would be fine with it, but it's just so much, I don't know. But what could we do? Well, I mean, the threshold doesn't give us much. Have a transistor shorted out on trigger release. You mean short short this capacitor, you mean? Not really sure how you would go about that. Like, could you describe it a bit more in detail? Well, maybe before jumping to conclusions, we could try putting in a trigger signal instead of using this push button. Maybe that actually makes a difference. I don't know. Let's see. Yeah, I'm also worried about the decay actually, because I would like to keep the decay, but of course, like, this is tricky because you would kind of need to This almost feels like programming, you know, you need like an if-else thing. You need to check like, okay, has it re-triggered yet? If not, then keep going, and once it re-triggers, then somehow like instantly dump the contents of the capacitor, and then true, Juanito, but I did put in the resistor to ground on the input. That's why it should actually not matter that much. But let's see how it works with a trigger signal. Okay. Doesn't seem to work at all. Maybe it's too low. Okay, weird. So I'm pretty sure that this should trigger. Let me try an LFO instead. Ha, that works, okay. Okay, you see, the annoying thing is that as I increase the frequency, the pitch of the drum increases. Okay, so I mean this is an okay kick sound here. It's kind of gabber. Let's increase the distortion. Buffer the gate before converting to trigger. It sounds really mean, actually. Okay. Let's play with the threshold a bit. Let's see what that does. Of course, it charges up the capacitor more, and that's why the pitch increases, basically. Release obviously also changes things a bit. I was thinking maybe... no, that also won't work. Maybe it does work. So my thinking, and I think this is the last thing I will try today, because we've already been at it for how many hours? 3 hours. So let me turn this down. So what I think I will try is the following thing. Just because like right now I'm on this trip where I always, when I have a problem, I always think of diodes for some reason. So I was just thinking maybe we can, like, my goal right now would be to decrease the value of the capacitor here, because right now we are using a 10 microfarad capacitor here, which is huge, and so it takes a long time to discharge this. And so what I'm just thinking of is it would be great if we could make the capacitor discharge very quickly in the beginning, but then take a long time after that. And just my thinking right now, and this is going to be overkill because we're going to need a lot of diodes. I hope I have enough. But what we could try is the following thing. So I mean, right now, what's happening is that we charge our capacitor through the diode, and then once the comparator goes low, this diode blocks, and the capacitor pushes its charge through the resistor here to ground. So it discharges. And the problem is that if the comparator's output goes high before the capacitor is discharged, then of course that will just bump up the pitch even more, because the capacitor gets even more charge, and then it just pushes up the pitch. And so what I'm thinking is maybe if we this gives me actually a separate idea. We could also maybe this is even better. This might even work better. Okay, level with me. Give me a second. Okay, so what we could try is we could try to not put these guys directly after our buffer here. So what I'm thinking is, I mean, this comparator at the top level pushes out 12 volts, right? And if we push 12 volts into our CV input of the filter, then of course the pitch is gonna jump like way up. And the fact that we're seeing with this big capacitor is that it's filled up and up and up till it kind of hits 12 volts, and then it hits the maximum level, and then it can't go higher, and that's the pitch ceiling. But 12 volts is going to be like very high, so we have a lot of playing room there. So what I'm thinking right now is, why not just use an inverting op amp here that we use as a amplifier with a gain, lower than 1. So my thinking here is basically that we take this spike that this thing puts out, and we just scale it down to, I don't know, maybe 3-4 volts, something like that. And this might actually give us, this might take away the headroom. So then the capacitor has like a set ceiling for the pitch, so then it's no problem if we always completely charge the capacitor. I'm just spitballing here. Maybe that's also stupid, but let's see what happens. So I will use 10Ks here. And okay, now let's re-examine how this works. So if you want to reduce the pitch, the resistor here has to be stronger than the resistor here, because and I like this metaphor kind of, you can think of it that if this voltage coming from here has to fight a stronger resistance than the op-amp's output, then the op-amp's output will have like an easier time to kind of equalize the voltage at this point, because since we are going to connect this one to ground, then the op-amp will be kind of in an equilibrium whenever the two inputs here are equal. So whenever the voltage here is 0 volts, then the op-amps, or near to 0 volts, then the op-amp's output will basically stabilize. And so the easier we make it for the op-amp to pull the voltage here down, the less gain it will have, basically. So in this scenario, the signal will be actually very quiet. Not by a factor of 10, I think a factor of 9, something like that. But this will divide it down quite a lot. So let's look at the signal that this gives us. So view this in a new scope, reset it, sorry. And right now it's not doing anything. I think it's because of the threshold, I guess. This is weird. I mean, yeah, this is way too low. Let's bump this up to, okay, no, there we go. And then we bump this one up to a 10K maybe. And of course this is inverting. Yeah. Okay, so we can't use it in the inverting configuration. My bad. Probably you pointed this out in the comments. I'm sorry. What we have to do instead is actually very simple, which is we just set this up as a buffer, and then we use a voltage divider. Simple. Move this here, go here, go to ground, and now this should give us a very simple scale down. Yes, now you can see it's maxing out at 5 volts, which for my taste might actually still be a bit too much. So which values do I have here? I mean, I think I will go, this is maybe a bit wasteful of current, but oops. I will go with a 10K 4K7 combination, and then we have 3.6 volts So, okay, let me check the comments. Maybe you've already told me why this is a stupid idea. Let's check. Yeah, true. I think if you plug this directly in the breadboard, this actually destroys the breadboard. So I shouldn't complain probably. Yeah, multimeter beeps. This is it's extremely annoying. Like this thing actually, if you use like if you do use it, like a few days ago, I was matching diodes, and like I mean I was using it, so I was changing the diodes and everything, but this thing doesn't care. Like after I think 15 minutes, it beeps like aggressively, and so you have to just turn it off and on. And I'm sure you can change the settings, but I've been too lazy to actually look that up. Okay. Yeah, Dylan, you mean like for breadboarding? Yeah, that's actually a great idea. I think that's probably the way to go. What I'm trying to do now is, I'm basically just my hunch is that the problem was that this comparator is blasting out 12 volts on every pulse. So whenever this goes high, you get a blast of 12 volts here, and I think the problem there was that this gave us too much headroom for the capacitor to be charged up. And so what I'm just trying to do is I'm trying to reduce that blast, and I try to reduce the voltage. So we set kind of ceiling for the maximum voltage that our capacitor can reach. And by that, I hope that we can kind of set like an upper limit, and then we can eliminate like this kind of, I don't know what the English word is. In German, we call it aufschaukeln. So, you know, like if you sit on a swing and you push it repeatedly, like you go higher and higher, and that's what happened with the drum sound. So whenever multiple triggers after one another came in, the pitch of the drum sound basically rose. And so what I'm trying to do is I'm trying to kind of limit that by setting a kind of like hard ceiling by doing this. So I'm capping the, as you can see here, I'm capping the pulse to be at 3.6 volts at maximum. So that's what I'm trying to do. And okay, so here the next thing will now be, oh, and this has the nice side effect that this is always at ground level once it goes low. So we don't have to worry about any negative voltages here. Okay, so put this diode in here, and then we take this buffer and we place it up here, and we connect it to this guy. And okay, we can see that this resistance is way too strong. Right, that looks a lot better. Okay, and now we can see that we have a proper curve. Oh, interesting. Look, it actually looks much more, and this is actually on accident, than what I wanted to achieve. But yeah, you can see that we actually have an attack, a quick attack, we have a decay, we have a sustain. I don't know where it comes from. Don't ask me. It's there. And then we have a release. So on paper, this seems like a great success. We have to build this and see if it actually is a great success. But okay, so I will switch back to the breadboard, and let's try to build this. And best case scenario, this will work out just fine. Worst case, let's see. Okay, checking the comments. What's good about my multimeter being smarter than me? Well, I mean, are you talking about digital, like smartphone based? I don't know. Okay. Let's try to bring this to the breadboard to kind of move this along. Okay, so I think right now I tend towards tearing this down. Oops. This is not good. Take this out. Okay. So why am I tearing this down? Well, basically, I find that oftentimes it's actually easier to start from scratch than to try and fix the mess that you've made. So let's just tear this all down. and then we can start fresh. Okay, so we know that all of this is actually fine. This comparator was also fine, so we can put this back in. I'm going to, not comparator, this voltage divider. So I'm going to connect this back to our inverting input right here. This will go here. And then we put that back in here. And now our comparator works because we didn't really change this, so this should still work. And then the next thing that we have to do is we need to scale this signal down, like you just saw me do, with the voltage divider and the buffer. And I will do this again in a very ugly way. I will just take a jumper. I will move from the output here. No, we need a diode. So I will take a diode and I will move from the output of this op amp to, that's actually also not right. Sorry. Okay, so again, I use this diode to go to a empty row over here, which you can crucify me for this horrible mess. I know I'm apologizing for the 50th time, but this is a mess just for the protocol. Okay, so we go to this empty row, and then what we do is we use a 10K to connect this row to the non-inverting input of this op amp right here. And then we need a 4K7, which I need to get. Give me a second. Okay. I'm actually very, very excited to see if this actually sounds okay. But I guess, long term, my plan anyway is to kind of polish this up, like make this into a proper thing, and then do a proper video on this. But yeah, it would just be fun if it worked right now. Okay, resistor to ground. That looks okay. And then also we need to connect the inverting input and the output because of course it needs to be a buffer. And there's crazy people in front of my house screaming again. Perfect. Actually, I often can't differentiate if they're just drunk or if they're actually crazy. Okay, so we set up the buffer. And now we basically play the same game that we did before. So we need another diode. The question is, do I have more diodes? Yes, actually I do. Perfect. Okay, so the idea is we want to connect the output of this op amp again to a, no, we can actually make our lives a little easier here. We just go to the non-inverting input of this op amp over here, because remember this will also be a buffer, and maybe I should switch to the simulation again just real quick. So just to show you what I've built right now. So this one, this stuff here, like I said, was completely intact, so we reduced it. Then I used this diode to go to this empty row to the right. Then I did the voltage divider at the op amp's non-inverting input. I configured this as a buffer. Right now I'm using the diode here to connect, the output of this op amp to the non-inverting input of the next op amp. And now all that we need to do is put in a capacitor and a resistor to ground. And then from here, we can actually just go to our CV input, and then we should see or hear if we, in fact, have something that works or doesn't. Let's see. Yeah, the results are sometimes the same, drunk and crazy, but I don't know, like, I mean, drunken people can still be in some ways reasonable. Like, people here sometimes, they just, I don't know what's going on. Actually, one time when I just moved into this flat, which, like I said earlier, is like very central area of the city, I was repotting a plant. So I took one of my plants and I took it into the backyard of this house, and I started repotting the plant, and I was maybe out there for like 10-15 minutes, and then I was done. I went back in, and just in the staircase there was just this guy who had like all his belongings like spread out like on the stairs, like all his stuff, and he was just smoking a crack pipe. And I was just standing there like awkwardly in front of him with my plant because it was blocking my way, and I was like, dude, I need to pass. And it was like really bizarre. It felt like a clash of life concepts in a way. Super weird. But okay, so we have the diode going to this op amp here, and now all we need to do is set up the capacitor that's going to ground. Hey, great to hear that you like it, actually. You left no comment. Actually, I plan to do as well. Like, it's really, I don't think it's worth it. You have to out crazy them. Yeah, I mean, one time I came home, it wasn't even that late, it was like maybe 11, something like that, and there was just a guy pissing at my door, just at not at my flat door, but house door, just pissing, and I couldn't open the door because he was standing in front of the door, and so I stood there, I didn't really know what to do, and at some point he noticed me. And then he just mumbled something, and he just walked away awkwardly, and it was such a strange encounter. And it was really like, that was maybe the point where I thought like, okay, really, I need to go somewhere else in the city. This is terrible. Okay, so I'm just using this jumper to break out from here because I can't fit the capacitor in there. So I'm going to break it out to there, and then I will use a 1 microfarad here. I will drop it in there, and then from here we need to go to ground. Boom. Prepare super circle with Tabasco. That's a good idea. I mean, yeah, it is Berlin, and I maybe my tolerance for this kind of shit has kind of dropped since the lockdown, because normally, it's like you can kind of balance it out with like cool stuff, like you have culture, you have cool cinemas, they show great movies. It's like a trade-off, I feel, it's like you take the good with the bad, but since the lockdown, it's basically just the bad in my opinion, which is kind of a bummer. Okay, so we have the capacitor to ground. Now all we need is the potentiometer to ground, actually, and I am going to go again with the 250k, just, I don't know, see if the value works. Okay, put this here, then we will need another jumper. Well, how is it in Los Angeles? What's the problem? Oh, 10 cities. Yeah, I've heard of that. It's like, I think I saw a report that actually, like, people that have a job and that would normally have enough money, like, they can't afford to rent a place. They have to stay in their car or stuff like that. Okay, plug this one in here, and then we need to connect that one also to the capacitor. We put this here, and let's pray that this works. I'm not sure actually, but I'm curious. Okay. No, that does not seem to work. Okay, so I went wrong somewhere, I guess. Let's re-examine this. Let's turn this down first and foremost. I don't want to annoy you. Okay, let's walk through it. So this part I think should be fine because we have the capacitor, we have the resistor to ground. This should be okay. Then we have our diode going to the first, to the comparator, I mean. We have the 100K to ground here, which should also be okay. We have the threshold and jumper on the... Ah, good eye, good eye. True. Maybe that fixes it. Let's see. Still nothing, unfortunately. Sound is still there, but the triggering does not work. Okay, but if I made one of those stupid mistakes, probably made another. Which one is not connected? This one is. This one also is. This one is. Ah, you know what the problem is? No, you're right. Okay, this is also not connected. It's actually not. It's not the root cause. Like this is also wrong. Yeah, true. But let's put this here. This is good. This is also good. Yes, this also works. But I haven't connected the output to anything. I haven't sent it to the CV, and so obviously it's not going to work. Okay. Okay, this is confusing. Let's see what happens if I send in the LFO. No. Okay, so something else is off. Oh, this is super annoying. Okay, let me turn this off. Okay, we will get this to work. I'm very determined. Okay, let's see. So the output is going to this row, and then from here we go through the 10K to the non-inverting input. We go with a 4K7 to ground, and then the diode, the output goes to the... this is not a buffer. This is not a buffer. It's missing the green jumper again. Seems like this is my nemesis today, setting up jumpers. Buffers, I mean, sorry. Okay, let's try again. At least it's not whining anymore. And this works, great. And now we try with a trigger. Here's something, I think. There's something there, but I guess it can't really count as a drum, so okay, that's super low. It's actually there. So what I'm going to do, like the voltage divider here, someone walking around upstairs, exactly. People seem to watch it on, yeah, I was amazed as well. Like I couldn't see it, but you could see it on the stream. It's like, ooh, crazy. Okay, so I think the reason why someone's walking around upstairs is that this voltage divider is too intense. You know, like I've dropped down the peak to 3.6 volts, I think. And so this is just not high enough to have a reasonably good sounding kick drum. So what I'm going to try and do is I'm going to turn this off because I don't want to subject you to unnecessary noise. I'm going to take out this 4K7 and I will replace it with a 10K for now. So we will just cut down the trigger by half. So it's just going to go down to 6 volts from 12. So let's see what that does. Boom, okay. Haha. Okay, let's try and turn up the frequency. Okay, it still goes up a bit. But it's actually, I would say it's really tolerable. Perfect, cool. Turn on the distortion. Play with the threshold. Interesting, that doesn't do much actually. Why does it not do much? It doesn't do anything. Weird. Huh. Doesn't change a thing if I turn the knob. Why is that? That's weird. Yeah, I will take it. Actually sounds good to me. Okay, so now last thing that I will try, drop down the resistance on the CV input of the filter. Right now it's sitting at 200K, and I will drop it down to 100K, just in hopes that the drum sound will get a little bit more clearly defined, maybe. It's actually too much. That's too much. I'm still wondering, like, why does the threshold not do anything anymore? That's so weird. But okay, maybe I won't take it. Give me a second. I'm gonna get another resistor. Okay, so we will try, instead of a 200K, which I think was just a bit too much, I will try a 100K and a 47K, just in series, so that we have, yeah, a pot would be a good idea, but I'm actually too tired right now to do that, because it's almost 10:30 here. So I will use, I don't know if that's going to work. Let's see. Going to use a resistor here. Boom, that one goes in there. And then a 47K. Is the LFO voltage input different compared to the button input? Yes, the LFO, I think it pushes out maybe 7 volts, something like that, and the button obviously was the button was 12 volts. Okay, so I think this is still, I had the frequency on the cutoff knob turned up. Okay, so this way we can actually also influence this. Cool. still wondering why the threshold does nothing, but of course it's okay. I think the gap is still a bit too high, so maybe raise this one up from a 47K to what else do I have? You know what? Let's just go for the potentiometer. Just too curious how that affects it. Okay, so 100K here, and there's not enough space there, so let's just wing it and do it like this. Oh god, this is getting to be like a horrible rat's nest actually. Oh, Jesus. Okay, mission accomplished, hopefully without breaking anything. And then from here, I will just do it like this. Okay. And then we go in here. And now it doesn't work anymore. Did I? No. Okay, I connected it to the right pin. That should be okay. Oh, this resistor is not in the right spot, or rather the pot is not in the right spot. Okay, perfect. So if we turn down the release, I think we can actually get a quite convincing drum sound. And of course the pitch goes a bit up on repeat triggers, but I think it's actually much better. And let's see how far we can push it. Oh, Jesus Christ. Okay. That's really mean actually. I think I would like to have a bit more release. This is a 250K, I think, right? Yeah. Whoops, sorry. So one final thing, I will replace the 250K with a 500K so we can have a bit more, we can have a bit longer release. Okay, let's see. Okay, then drop this down again. Okay, I would say it's acceptable, probably. Jesus Christ. Okay. I mean, of course, the values need to be tweaked, definitely. But miraculously, this kind of works. Okay, perfect. So I'm going to turn this down. Okay, so let's check if you have any questions. That crunched, yeah, I agree. It's very crunchy. Have you seen the 80AR? Actually, in my rack I have 4 of them, but I've built them before I had any idea about circuits at all. So I just built them from the schematics. So I haven't really looked at how it works yet. So it might be very similar. True, yeah. Okay. What are you feeding it? I missed the beginning of the show. Well, I mean, this is basically just the filter in self-oscillation mode. And then what I did here was basically just kind of scramble together an envelope generator that is now triggered by an external signal, and then it puts out a shape that sounds kind of drum-like. That's the idea. You should label the distortion of Jesus Christ. Yes, I will definitely do that. Okay, Max, bye-bye. Thanks for watching, definitely. James, self-oscillating diode filter. Yes, exactly. So it's just oscillating on its own, and the distortion that you heard was basically just by driving the diodes. Like whenever you push them too far, then the sound gets like this kind of gritty character. That's basically the idea here. Michael, goodbye. Hopefully see you soon. Is the trigger a gate? Yes. Basically what I've done is I have first built a gate to trigger circuit. So this kind of can take any kind of gate length, and it will transform it into a trigger signal, and that trigger then triggers a second stage, and this second stage then charges and discharges a capacitor, and that kind of creates the voltage curve, and that's how this sound comes about. Where do you have your knowledge from to build those circuits? Actually, you just saw like where I got my knowledge from. It's exactly this. Like this is all that I've ever done. It's just I bought a breadboard, I bought some components, and I just stuck them in there, and I just tried stuff. And then obviously I looked at other schematics on the internet. I built stuff because I was impatient. Just wanted to have some modules, and then I was just asking myself, okay, so how does this all work? And then I started playing around with components on the breadboard, and you just saw my process. This is how I do it. It's not very sophisticated. I don't have like book or like university knowledge. It's really just I think the idea is basically I know what I want to hear. Like I know what I want the kick to sound like, and then I just throw stuff at the breadboard until it sounds vaguely like how I want it, and then I refine it, and at some point you have something that sounds how you like it. Okay, anything else? Suggested read for everyone interested in analog drum design. Which one? Did you post anything I didn't see? Sorry. Thomas Henry. Yes, I've heard that that's good. Actually, I haven't read any books, but I might pick something like that up. Thinking about starting out. Yeah, probably. Op-amps can never go wrong. Yes, Pedro, I agree. I think this was fun. I'm going to try to do this more often. Okay, guys, any more questions? Have you experimented with guitar amps? No, actually, you mean building some? I have thought about just doing a kind of distortion pedal, just with the transistor distortion, but haven't gotten around to it yet. And also, I only have a bass here. I don't have a guitar, so I would have to try it with a bass, maybe at some point. Did you ever burn anything in your modular when fiddling around with the breadboard stuff? Surprisingly not. Even though my modules are very shoddily built, at least the ones that I have in my Cosmo, the Look Mom No Computer format modular, like those modules are terrible. They don't have any protection against reverse polarity. It's a mess. It's really a mess. And also one thing that you might find interesting, like I've done this video on this power supply, which, by the way, it's completely not my design, so I can't take credit for it. It's just it's basically the who was it? Music from Outer Space power supply, which also kind of inspired, I think, the Frequency Central power supply that you can buy. And so I bought one of those, and I powered it with one transformer. And at some point, my modules started dropping out because they didn't get enough current. And then I just decided to build another power supply, but hook it up to the same transformer. And now in my box, I have actually 4 of those power supplies who are all hooked up to the same transformer. And I did this when I was very naive and stupid. I don't know why it works. It works. The transformer can supply, I think, just like 1 amp or something like that, a bit more. And I don't know why that works. It works, but don't do this, please. Okay, and yeah, no, I didn't burn anything, so it never, nothing has kind of broken so far. So fingers crossed there. One day I was experimenting with transistors, resistors, and condensators. You mean capacitors? And my sound just sounds like a bird. Yeah, that happens. True. How many op amps are in use in this circuit right now? 5 on this side, up here, and then I am using 3 down here. Probably you could somewhat cut down, but that's what it is right now. You should come to The Hague to give some workshops for the sonology people at the Royal Conservatoire. I have no idea what any of that is, but once Corona's over, I'd gladly go somewhere and give a workshop, sure. Thank you for sharing all the knowledge. Thank you for watching. I mean, first and foremost, it's actually great that I can do this and have people be interested in this and be willing to watch me do this stuff. So thank you for watching this, like seriously. May I ask you what's your profession? As a physicist, I really like your visualization. They're really accurate. Thank you, even though you're not using formulas. Thank you. My profession, it's a kind of a jumbled path, actually. In the very beginning, I studied computer science for 1 year. I decided that doing that at university was really just not for me. Like I couldn't deal with kind of school-like structure. You know, like for me, programming was always fun. Like I used to do it, you know, at home. I used to write like my own terrible little video games. And then I went to university and it was all like, oh, you have to learn all these formulas now and you have to do all this math. And I was like, ugh. I don't know, it just didn't feel right to me. Also, I failed a test, I think 2 times. And once you fail 3 times here in Germany, you're out forever from that specific subject. So I said, no, fuck it. I'm going to do something else. And then I first did media studies, got a bachelor's degree in that. Then I studied film for a short while, and then I settled on, it's called cultural studies here in Berlin. It's kind of this mishmash of like philosophy, sociology, like all the kind of stuff. And funnily enough, like at some point I also got fed up with that because it also got so academic. Like people were so hung up in like knowing all their shit, and you know, everyone's talking about, oh, have you read this text by Foucault, and have you read that French guy, and it just got so self-referential and kind of useless that in the end, like when I wrote my master's thesis, I was just like, nah, like really, it's not fun anymore. And so I kind of went back to my roots, and I decided to go back to programming actually. And now I have a full-time job as a front-end developer, which is very fun actually. I really enjoy programming. So that was a good move. And also the upside is that if you work in IT, you actually like people actually need you to work for them. You know, as a cultural scientist, it's more like you have to always beg to get a job. But in this field, it's like in the IT field, it's just much easier, and I really enjoy that. Okay, what's more? How would you approach making a line output for headphones? Get this question a lot. I think basically what you want to do is you just want to make sure that your maximum voltage swing is limited. So if you go to Wikipedia and you Google for line level, you will find that there's basically 2 different standards for line level, I think. One is for kind of consumer electronics and the other is for professional equipment, whatever that means. I think the one for professional is, I think I have to lie now, but it's maybe 2-3 volts. No, more. It's like 4 volts peak to peak, something like that, maybe a bit more. And then consumer electronics, it's 1 volt peak to peak, maybe a bit more. And so kind of depends on what you're targeting. I think the idea would just be make sure that your circuit does not go over the threshold. So by all means, make sure that you not exceed that level, and then I think you should be fine, probably. Okay, what else? Thank you for doing this. Thank you again very much. Thanks. I love to hear that you enjoy the diagrams. Thanks, James. Thanks a lot. Great that I can help with your report. Actually, that's great. What are the diodes? The diodes are just generic 1N, 4N, 1N, 41, 48. It's just like these standard switching diodes. They're box standard. You can find them anywhere, basically. Okay, just an idea for the next stream. You can stream directly from Discord. You mean from Discord to YouTube? I'm very new to this stuff, so yeah. So using one of those rectifier cap linear regulator setups is making use of virtually none of the available power before it will drop out. Ah, okay, good to know. Good to know. You spent a lot of money on this, Holly. So I've been robbing you. I'm very sorry. Thank you again. Thank you. Okay. What else? I studied electronics. Man, was that boring compared to hobby stuff. Yes, I completely agree. I mean, it's what I just said about the programming stuff. I think once you get out of the restrictions and you can actually improvise and do stuff yourself, it's so much more fun. True. I also started a lot at university. Now I study interactive media design at the University of Applied Sciences, and that's so much better. Yeah, I can relate. Good for you. Gotta go. Yes, goodbye. See you soon, hopefully. Let's see. What else? Enjoyed the stream. Very glad you enjoyed the stream. Love the little mistakes and crazy people outside. Yeah, I mean, maybe they heard the gabba drums and just thought like, oh, that's a great place to party. Creating a 1 volt peak to peak line voltage and plug that in. Yes, exactly what I said. That's true. It was entertaining. I was actually worried that it might not be entertaining, but it's great to hear that it was entertaining. Okay. Since how long have you started doing synth electronics? I think now it's 2.5 years. That's when I started 2.5 years ago. I can show you to do it next time. Yes, definitely, please. We'll just text and then we see. I built a circuit with a sound module out of a toy gun. Actually, yeah, like circuit bending I think is super fun. Like in the beginning I also played around with this. Like I bought this really shitty little keyboard from the flea market, and I just shorted stuff, and it was very fun. I think it's a good starting point, definitely. Yes, I will also make sure, I mean, this, like I said earlier, this live stream, like the recording will be on my Patreon. I will also publish the Falstad link. I will try to take this circuit and, completely document it in Falstad, like in the simulator, and then put it on there. Okay, do you have a favorite store for buying all the parts in Germany? Yes, definitely. There's this store called Segor here in Berlin. Which is like a very tiny, small shop. They also ship stuff, so this might also be an option. They have a very good inventory. They usually have all the stuff that you need, and I could just recommend this. And I think it makes sense to support small businesses and not always go to Mouser or the big companies. I've got a ton of 74 LS series chips. You mean op amps, TL074? If so, then yes, they're perfect for audio. Next time some IC should definitely burn up electric rooms there. Yes, maybe I will go for that. It might be unsafe, but yeah, let's see. Will you ever build a compressor? I've thought about that a few times in the last few days. So yeah, I think that's something that I'm going to do. But the next video is already laid out. So the next video is going to be on my Eurorack module that I've built. I can't show it right now because it's in my rack, but you will see that. But after that I will do a VCA, and then maybe VCA. Maybe we could do a VCA with like a built-in compressor. Let's see. Okay, what's the name of the shop again? It's Segor. I'm going to put it in the chat here. That's the name of the shop. You can find it. We have no small shops here anymore. The big companies killed it all. Yeah, that's exactly the reason why I like to support the small shops. Because I think it's just a nice experience to go into the shop, look at all the parts, pull the drawers out, look in. It's nice. There's CMOS logic chips. So you're talking about the inverters. Well, there's a problem there. If you try to build along with my videos, especially with the oscillator, like I use the 4106 hex inverter, and I use that because it can handle big voltages. It can handle, I think, 15 volts, and the 74 range, I think they can only handle like 5 volts. So the logic level, and so you could still make it work, but it's gonna require some changes to the circuit. So I always recommend to go for the 4106 just because it's easier. Yes, the 70 series logic ICs, exactly, true. Where did you find info on the other line level voltage? I think it was just on the German Wikipedia. Wait, I will pull up the browser window here. And I'll just pull this up here. Oh, I think it's actually on the English one as well. Here you can see professional audio is 3.472 volts peak to peak, and then consumer audio is 0.894 volts peak to peak, which I don't know why they chose those values, but probably has something to do with the decibel values, I guess. Okay, you will try Zego 2. Great, cool. Radio Shack Berlin. I think I've heard the name, don't know what that is. Salvage old PCBs, do it all the time. Yes, probably a good idea. Do you have any simple sine wave circuits that can be FM'd and somewhat stable? Not yet. Sine waves are my Achilles heel for now. So the circuit right here, the diode ladder filter, actually works as a sine wave oscillator if you put it into self-oscillation mode. And I've tried a few days ago to kind of play with the resistor on the CV input. And if you tweak this, you can actually get this to track. I got it to track over, just tried it quickly, but in that instance, I could get it to track over maybe 1.5 octaves. Maybe with more fine tweaking, you could get it even better. But it's not a real solution. It's just something that I have right now that you could try. Yes, circuit simulator is definitely a lifesaver. Definitely. Radio Shack is like Conrad. Okay. USA joke. All the Radio Shacks are gone, so no more browsing parts are when you need them. Yeah, that's the way of Blockbuster, no? Like same thing. Actually, it might sound crazy, but back in the day, actually, I enjoyed going to the here we call it videothek. Where you go and you rent DVDs. I actually enjoyed, like walking through there and looking at all the covers and, picking something out and then maybe not getting something because someone else has rented it already. I don't know. It's maybe weird kind of pleasure, but I liked it. Sine wave is pretty darn hard. Yeah, I guess. I think I have it in the back of my head that you can convert a triangle wave into a sine wave. Like I don't mean filtering, I mean like proper conversion. And then, of course, you can just build a triangle wave oscillator and just convert it. That should work, I guess. But, creating the sine wave itself and having it track perfectly, probably harder. Yeah, true. Does fuse of the JRC4558 can make the job? Not exactly sure what you mean. Last time I was in the videothek, they had VHS. Yeah, that must have been fun too, no? And then somebody taped it over and you get to watch like their family videos or something. Started a year ago, and this gives me hope of actually advancing with my stuff also. Definitely, just don't give up. I think if you're having fun, like if you're having fun trying stuff out and bug fixing and troubleshooting, then you're definitely on the right path, and then I think we're gonna make progress. And at some point, I'm still struggling with this, but I hope that at some point it's like learning a language, and then always for a problem, the solution. Maybe you kind of saw like the beginning of that today. Like, you have an issue, okay, this voltage here is too high, the capacitor gets charged too much, what can we do? Well, we can limit the voltage, blah, blah, blah. Like ideally, I would like to be more flexible in this and have more approaches in my belt. But I think this will come down the road. So yeah. Resonating filters can be used as sine wave oscillators, and with good expert converter, they can track very good. Yeah, that's true, definitely. Converting triangle wave will not be as perfect, probably, yeah. Sine waves can be obtained from triangle wave through nonlinear distortion, Ray-Wilson. Yeah, I think I saw it there too, true. Are you able to list all of your parts after this is done? You mean all the parts that are lying around here? Or you mean just the parts that go into this circuit? I mean, like I said earlier, I'm going to whip up a complete recreation on Falstad, so on the circuit simulator, and then you will see in there, you will see all the parts that are necessary. But like I also said, I'm going to anyway like polish this up and then make a proper video about this, where I tweaked all the values and have it like kind of presentable. So if you want to wait for that, then that's also coming. I think Music from Outer Space implements LM13700 OTA to convert triangle to sine by distortion. Might very well be, I don't know. Shout out to Farnsworth Electronics, Waterloo, Iowa. Brick and mortar store still exists. Thank you. Yes, perfect. It's a great thing. I would like to see you build a voltage controlled resistor, not the slow LED photoresistor solution. I feel like that's kind of like the golden goose that people kind of chase when they start out with synth DIY. Because I mean, I get it. Like it's like the perfect kind of scenario. Like if you just had a device that you can just plug in anywhere and have it be a voltage controlled resistor, it would make a lot of stuff easier. But I honestly think it's not doable without major drawbacks. So you can use an OTA, like an operational transconductance amplifier. I think you have to use 2 to actually make a proper floating voltage controlled resistor. But I think it has its limitations, and it's a lot of stuff to set up. So generally, like what you find, like if you look more into it, you will find that this is like the one thing that a lot of synth designs like build around of. Like everyone has this problem, and then they all find different kinds of solutions. And for this filter, like the diodes are the solution. But for the Moog filter, for the Moog ladder filter, for example, they use transistors for that purpose. And of course, in the MS-20 filter, they use the OTAs, the operational transconductance amplifiers. But I think on the positive side, this is what gives a lot of filters and designs their own sound, because they all have to find a way to kind of replace voltage controlled resistors, like to find a different way to do it. So, and also a lot of people on this topic, a lot of people will tell you that you can just use a JFET, but I've heard this so much, and I've actually Googled a lot, and I've tried to find good examples of, for example, filters implemented with JFETs, and I couldn't really find anything. And I suspect that the problem is that I won't dive into it too deep now, but the problem is that for a JFET, you set their resistance value, if you will, by applying a voltage to the gate, right? But the problem is that the voltage at the gate will only determine the resistance in relation to the voltage at the source terminal. So if you send an oscillation through the JFET, then the problem is that the voltage at the source is oscillating, and that's why you can't really stabilize the resistance. I mean, correct me if I'm wrong, but that's, I think, might be the problem. And maybe you can solve this by, scaling the oscillation down like very much, but I don't know. Like I said, I haven't seen any good circuits using JFETs, so they have the limitations too. Most op-amps will work, yes, definitely. An op-amp, of course, there's different approaches to op-amps, but generally an op-amp is an op-amp. Just try it and you'll see. How I do it once my breadboard is done, I make the schematic from it. If you just build the circuit with trial and error, yes, definitely afterwards. It's a good idea. Here is the paper about sine wave. Voltage control oscillator with sine wave. It's not a link, can't click it, so you might have to provide just a search term to search for it. Thanks for the tips. I started just a few weeks ago with no electronic experience at all. Your videos really helped. Very glad. Thanks. Yeah. Again, thank you for watching. It's so great. There are digitally controlled potentiometers. Definitely, you can use those. Just for my personal preference, I don't like to do that because it's too easy. But you can definitely use those, definitely. And there's no shame in using those. So if you want to use them, go ahead, do it. It's more about voltage controlled current source. You mean for controlling an oscillator? Not quite sure what you mean. I just look up some of these IC model numbers online. Okay. There is a triangle to sine converter using diodes in the Falstad diode circuits menu. Yes, I think I saw this one once. I nailed it with the JFETs. That's great to hear. It was just a hunch. I didn't know. Some phases, which are basically all pass filters, are built using JFETs. Like the phase 90, but the JFETs must be matched. Yeah, this is also one thing. I mean, also in my filter here, I think it's best to match the diodes. I like for the breadboard, I didn't do it. For my module that I built, I did it. Honestly, I can't say that there's so much of a difference in the sound. Maybe I'm just ignorant, but both sounds okay to me. So, but yeah, true. I mean, for many circuits, you have to match them because it's really dependent on the components to behave the same way. So yeah, it's also a bottleneck with using transistors for voltage control. But yeah, okay, guys. So I am going to end this stream. And we've gone 4 hours, actually, which is quite impressive. Didn't expect it to go this long. I must say it was quite fun. I hope you also had fun. I hope you learned something. And like I said, this stream is going to be available on my Patreon. And I will also post a working simulation there. I will post a bill of materials there. So if you want to check that out, you can go there. If you don't want to spend any cash, you can also wait for the final video that I will, of course, make available publicly. You can check that out there. And yeah, that's all I have for now. Next video is going to be on improvements to this filter and also on the module that I built out of it. And I decided to do a giveaway. So I will give away 2 of my diode ladder filter modules as Eurorack modules. I will think of a way to kind of give them away fairly, but that's the plan for that. So stick around if you want one of those. And yeah, it was great fun. I will do this again. I hope you will join me again. And yeah, we'll talk to you all soon. So goodbye, guys.